So I apologize for being slightly spacey at the moment. It's about just after 7 o'clock in the morning in Australia, where I live, and I only flew in yesterday, so I'm still a little bit kind of not quite sure where I am. I'll get better as the afternoon goes on, I promise. So this presentation, this tutorial is part of my series of BGP presentations. Those of you who have heard bits of these before probably know that I do 3 of these. The BGP techniques one, a multi-homing tutorial, and a troubleshooting tutorial. And I tend to wander around the world, different network operations groups, giving these tutorials to the folks who, what happened there? Giving these tutorials to the different operations communities. So this is BGP techniques. It's kind of split into 2 pieces. I am occupying 2 90-minute slots this afternoon. So it is kind of split into 2 pieces. The first 90 minutes or thereabouts, probably slightly less than that, goes through a lot of the introduction. It's not an introduction for absolute beginners. It's an introduction more to the level of reminding you of the main aspects around about BGP and the attributes and this type of thing. The second half of it is more looking at deploying BGP within the network. So it's looking at how you go about deploying BGP within a service provider network. And more often these days I find within a lot of, well, other commercial networks, enterprise networks as well. And I'm also going to spend a bit of time looking at some of the new things that are coming in BGP that will be scattered throughout. I'm also going to look at some of the issues that I see facing the internet today. I mean, no doubt there are lots of other issues that are facing the routing system as well, but I'm going to look at some of the ones that I think are causing us to feel a bit more pain than we need to. I didn't introduce myself. My name is Philip Smith. I work for Cisco. This is by no means a Cisco presentation. It's pretty much a generic BGP presentation. I have got 1 or 2 configuration examples lying through this, more just trying to explain stuff than anything deliberate. If you've never seen Cisco IOS before, I apologize for that, and I hope that you can translate what you see into your own favorite vendor configuration language. But I say it's generally there are no configuration examples in this. Presentation slides, I hope they're on the NANOG website now. If not, they're up at the URL I've put on the screen there. It's about a 3.5 megabyte file, so be a little bit careful when you're trying to all download it at once, at least careful on the wireless network. If you'd like to ask questions, please do so anytime. I really don't mind being interrupted. Some of these presentations end up being really interactive, so I don't get half of it done, which is a good thing because then we can have a lot of discussion about some other things to talk about. And if you all want to sit and listen or just sit and do your email, that's fine as well. But if you do want to ask questions, because this is being recorded, if you'd please use the microphone and at least say who you are, and optionally who you work for if you want to do that, but at least say who you are for the record. So what we're going to try and look at least for the next half hour or so, we're going to have a look at some of the basics in BGP, so covering what BGP is and looking through some of the attributes. As I said earlier, we're going to then have a look at some of the scaling issues with BGP, a brief touch on using communities. I'm not trying to steal the BGP communities tutorial tomorrow. We're just going to talk about service providers, communities, and so forth. This is just a light introduction to it. I could spend days and days talking about communities if I really wanted to. This is just a light touch, a lot more detail in tomorrow's tutorial by Richard Steenberger and so forth. And then the final part will be more about the deploying BGP in the service provider network. Anyway, today, the first part is having a look at what BGP is, what it's all about, and some of the attributes. So BGP is a routing protocol. It's a routing protocol used to exchange routing information between different networks. By network, I mean a separate obvious entity, a business, collection of routers, switches, whatever, devices used to join different bits of equipment within their own network and to other parts around the world. It's what's called an exterior gateway protocol. That's probably old-fashioned language for basically a routing protocol that's used to talk between devices sitting in different networks. The RFC that describes BGP has been updated. This was updated last year. It's now RFC 4271. Those of you who have been around for a long time, like me, will probably remember RFC 1771 as pretty much the defining RFC for BGP. But in typical fashion, the RFC more or less came out first in the early days, and since then there have been a huge amount of improvements and additions made to BGP that really left the RFC badly lagging. At least it's quite interesting sitting on the vendor side of the fence, because you get all these RFPs coming in that says, hey, we want your BGP implementation to be RFC 1771 compliant, and that causes a bit of consternation, because if it was, it probably wouldn't work awfully well. So 4271 has massively updated the original RFC. If you want to read about an implementation report, if you're interested in implementing BGP yourself, you can read about experiences in 4276. And if you want to read some of the operational experiences using it on the network today, you can read about that in RFC 4277. There's a couple of them, a few more RFCs going over some of the background and bits and pieces of BGP. The autonomous system is basically a fundamental requirement within BGP. All BGP speakers rely on this autonomous system concept to function. And AS is used to uniquely identify networks with a common routing policy. So to put it in a nice picture, it's the collection of routers that you run in your network. You'd call that an autonomous system. You generally have a single routing protocol sitting in there. It's usually under single ownership, trust, and administrative control. So it's you as the network manager, network operator, whatever. It's a way of describing your routers. You get some circumstances, some situations where an autonomous system is shared between multiple networks. Some parts of the world, they seem to do this because it's, well, considered, well, you only need one AS and just lots of different ISPs will share that AS, as though there's some shortage of AS numbers or something. Autonomous systems are identified by a unique number. These numbers are unique in the internet, and that way you identify each individual network within the internet today. Currently, the ASs, or at least up to now, the AS numbers have been 16-bit integers. The first 64,500 or so are for use on the public internet. There are another 1,023 which are for private use. So a bit like public address space and private address space, the public AS numbers are for use on the internet. The private AS numbers are for use within your own network. And the first and the last AS number were reserved. It's just in the traditional fashion there. But ASs have now, or at least the AS number range has now been extended to 32 bits. So rather than 65,000 AS numbers, there are now 4,000 million AS numbers, or 4 billion AS numbers, or a bit over. RFC 4893, which came out a couple of weeks ago, I think it was about a couple of weeks ago, that actually describes the 32-bit AS numbers. It's been languishing as an internet draft for the best part of 5 years, as far as I remember. So it's finally been published as an RFC. 4893 is the one you want to have a look at. That being done is fine. The actual way that the AS numbers are represented on routers and configurations is still under discussion. Some people are quite happy with the 32-bit notation, so we just carry on 65536, 65537, 65538, which is fine at the moment. I mean, we're quite comfortable with those numbers. It's once it gets into the millions and so forth, I think we might have a bit of an issue. For that reason, George Michelson at APNIC had proposed a 16-bit dot 16-bit notation, which at least makes it a little bit more human readable. But of course, this causes some issues with well, regular expression matching the actual representation on the router configuration. So this is why it's still under a bit of discussion. The internet draft you wrote has now expired. I'm not quite sure really what the status of all this is, but I do know that the implementations out there actually tend to be supporting this sort of notation. So that's still kind of work in progress, but it doesn't actually break anything so far these days. Also, those of you who are already part of networks or aware of the internet routing table, you'll notice that AS23456 will be popping up. I mean, there's 6 instances of AS23456. This is not a problem, because AS23456 is being used to represent 32-bit AS numbers in the 16-bit ASN world. So that's something to be aware of. I mean, one thing I do in my spare time is, produce a routing table report that, I send to the NANOG list amongst lots of other mailing lists. And what that does is have a look at, basically the amount of aggregation and deaggregation and the size of the routing table within each registry or regional internet registry region around the world. It's kind of a CIDR report, but going into a lot more detail on a per registry basis. And every now and then, when the 32-bit AS numbers first appeared on the internet, I was flagging this as an issue, and now actually flag the number of 32-bit ASs that we are actually seeing out there. So be aware of this. You'll see more and more of AS23456 appearing in the internet routing table. AS numbers you get from the regional internet registries. So by and large, in this part of the world, North America, you'll be getting that from those from ARIN. You could also get them from your upstream ISPs if they're a member of one of the registries. So if you're not a member of a registry yourself, then you can generally go to your upstream ISP and they'll get an AS number for you. Just be aware that it's still your upstream ISP's AS number, not yours. Current 16-bit allocations have up to 44,000 have been made. Predictions are that we're going to run out of the 16-bit AS numbers round about, I think Jeff Houston was saying, October 2010. So it's still a few years down the track, but it's been quite a steady target that we're heading for. So it's around about October 2010 that we'll actually run out of the 16-bit AS numbers. Growth rate has been pretty steady over the last 5 or 6 years, which is quite interesting. Around 25,500 of these are visible on the internet. Why the difference? Where have the other 19,000 gone? Well, some of the 19,000 have basically just disappeared. Some of these organizations, they got an AS number in the big boom days in 99, 2000. They went bust in 2001, and the AS numbers probably just disappeared. Other AS numbers just are not visible in the general internet routing table. For example, there may be internet exchange points set up. They need the public AS number to peer across the exchange point, but the AS number is not visible through the ISP's transit provider. I see that happen quite a bit in the world. So those are generally why you have this discrepancy between what's being delegated to the registries and what you actually see on the internet routing table. The registries have also received 1,024 of the 32-bit AS numbers each. Around 5 of these, there were 5 of these when I was making the slides 2 weeks ago. 5 are visible on the internet. So these are the early adopters, mostly folks who've got early implementations of routing software that supports 32-bit AS numbers, trying it out just to see what happens. Anyway, so you can find out about these at the IANA assignment list. And there they list all the different AS numbers and which registries they've gone to and so forth. Now, let's take a look at some of the BGP basics, just some of the terminology. BGP session is generally set up between 2 routers, in this example between router A and router C. These routers would peer with each other. So that's just the basic act of setting up a BGP session between 2 devices. The BGP peering runs over TCP. It uses port 179. The classic early mistake that a lot of people make is that, they set all this up and they've got a nice firewall sitting in between here because Firewalls imply that your network is completely secure and safe from the outside world, and they don't allow TCP port 179 through the firewall. And so they sit there and puzzle, a lot of puzzling while BGP doesn't come up. So it's really important, if there's any filtering or any type of firewalling that's running between these two networks, to allow the TCP 179 port through the firewall. BGP is a path vector protocol, basically relying on the AS path. I'm not going to go through what a path vector protocol is. It relies on incremental updates. So in other words, if anything changes with the network, BGP will send an update. If you consider it the other way, if BGP sent the full routing table each time there was any change in the network, you'd have a severe problem. The routing table today is 222,000 prefixes, in my view. Sending that update, well, you send the update over an Ethernet link, it'd probably take a couple of minutes. Send it over, say, a WAN link, well, okay, this part of the world is not so much of an issue. Some parts of the emerging internet, you're still looking at multiple kbits per second links. It would take, well, a lot longer. 15, 20 minutes is I've seen for some of these. So incremental updates is kind of how BGP propagates any changes within the network. And the fourth point there, you have a concept of internal and external BGP. I always sort of dither in the operational world of trying to explain this as, well, BGP really is two routing protocols. There's an internal BGP which runs inside your network and an external BGP which is used between different autonomous systems. And I think it's quite an important distinction, especially for some of the stuff we're going to be talking about a lot later on. Now, another concept, demarcation zone. The demarcation zone is really the bit of network that sits between these two autonomous systems. Different people have got different names for it, but it's generally the shared network there we call the demarcation zone. So you see that term used quite a bit. BGP's general operation is by learning multiple paths via internal and external BGP speakers. So an internal BGP speaker is a router inside your network. An external BGP speaker is a router in somebody else's network, an adjacent network. BGP will pick the best path and install that path in the forwarding table. How it picks the best path, we'll cover in a little while. The best path is also sent to external BGP neighbors as well. So the router will figure out the best path, and it will tell its neighbors what the best path actually is. The way you implement any policies, and I'll define what policies in a while, but the way you implement any policies, the relationship between you and your other autonomous systems are purely by influencing the best path selection. The best path selection is a set of rules. The way you implement policies between your networks, between you and your neighbors, is by changing some of these particular rules. Now, the difference between external and internal BGP. BGP is used internally as IBGP, usually a small I, some people use a large I, and externally EBGP, small or large E. As I said before, I like to see these or consider these as two different routing protocols. I mean, even though they're using the same thing, the configuration is more or less the same, it's useful for a service provider when they're designing, building the network to consider them separately. If you look at IBGP, it carries some or all of the internet prefixes across an ISP backbone. So, for example, if you're talking BGP with another ISP, you'll learn all prefixes from them. How do you tell other routers in your backbone what these prefixes are? You would use IBGP to distribute these prefixes. And it's also where you put your customer prefixes. You're connecting customers to your backbone, whether it's a data center or whether it's fixed link going to their site. The address block that they have, you would pop that into your IBGP, and IBGP would be used to distribute that across the network. There's still some people in the world who believe that using OSPF and ISIS is a wonderful way of doing this. Those are the people who have not discovered that the network will not scale. And it's usually after they have a major network breakage or network outage or wonder why the network won't recover after a backbone failure, or at least it won't recover within seconds after a backbone failure, that they actually revisit the whole architecture and realize that this is the way things are done. So this is the function of iBGP. eBGP is used to exchange prefixes with other autonomous systems. Now these prefixes are generally the address block that you, as a service provider, will have received from the registry or the upstream ISP or wherever you got it from. And it's where you implement your routing policy. It's very rare to implement any kind of routing policy within iBGP. Okay? Notice your customer prefixes generally are not handled by eBGP, assuming your customer address space comes out of your own address block for following that model. If you've delegated address space to your customer, you're not going to announce the individual pieces of your customer address space to the internet. You're going to be announcing your entire address block. So there are some differences there. So the model representation could be something like this. Your interior routing protocol, IGP, whether it's OSPF or ISIs, is generally used so that your routers can find each other in the backbone. Once your routers have found each other, you can use iBGP to distribute prefixes you've learned from outside your autonomous system or prefixes from your customers across your own backbone. And then we use external BGP to distribute the prefixes between the different autonomous systems. I've kind of used this model to try and explain it as a bucket concept, and eBGP is used to move prefixes from bucket to bucket or AS to AS. And that model's been used, well, I don't know, I've used this model since 1994 pretty much from my ISP days. But I know that it's taken some people a lot longer to actually go over to using this. iBGP was a kind of, oh, do we have to use that? We'll just use OSPF for everything inside our backbone. And then when people have to actually try and do transit, then they end up doing really weird stuff just to try and maintain the path across the network. But this is really the only accepted way of doing it. I often wonder whether it's really any point showing this slide, but then I find quite often I've got to go and explain this slide in more detail afterwards. But this is what ISPs are generally doing around the world today. So we look at external BGP peering. By definition, the BGP speakers are in a different autonomous system. So for example, we've got router A here connected to router C. The way I've drawn that is just some kind of Ethernet connection. So router A and router C are directly connected to each other, and they'll be using eBGP. The AS numbers are different. AS100 talking to AS101. They should be directly connected. Notice I haven't said must be, because there are some exceptions. They should be directly connected. The reason is that you're never running any other routing protocol. You don't want to be running OSPF or RIP or ISIS between different autonomous systems. An interior routing protocol is, well, interior means inside. So interior is definitely not here. Interior is inside that or inside that, not in this point here. There's still some ISPs who are using interior routing protocols to have the connectivity between the ASs. And even though I go through all the horror stories and so on that I've suffered in my past of people trying to do this, they say, oh yeah, but it works. Well, and if it works, why should I bother changing it? Which is, well, not really, not understanding the accidents that can happen with an OSPF running there and an OSPF running here and choosing to run OSPF on the inside and having all the prefixes bleed from this OSPF into that one and the issues that can cause. Henceforth, you really want to have the external peering routers directly connected to each other, whether it's on a shared Ethernet, shared point-to-point link. That's really the only way to try and do this. Internal BGP, the BGP peer is within the same autonomous system. So all the BGP speakers have the same AS number. Unlike eBGP, there's no requirement for these speakers to be directly connected, because you're going to use your interior routing protocol to find all your neighboring routers. That's the whole point of running an OSPF and ISIS in your backbone. It's so that all the routers can find each other. Okay, so your IGP takes care of the inter-BGP speaker connectivity. So all the internal BGP speakers need to know is the address of the remote iBGP speaker. The next requirement is that iBGP speakers have to be fully meshed. Well, okay, they don't absolutely have to be, but that's starting to get into really tricky configuration. But as a general rule, they need to be fully meshed, because internal BGP speakers will only originate networks that are connected to them. So if you've connected a customer to your router, you will originate that customer's prefix by iBGP into your backbone. And they'll pass on prefixes learned from outside the autonomous system. So if you're speaking to another autonomous system, you learn prefixes from them, you use iBGP to distribute those prefixes across your backbone. An iBGP speaker will not take a prefix learned from another iBGP speaker and pass it onwards. That's the default behavior of iBGP. Now, this was fine way back in the early mid-90s because our networks were very small then. When UUNet's backbone, and at the time I was talking about, was what, 50, 60 routers? And our part of it, when I used to work for UUNet before I joined Cisco, our part of it in the UK was probably about 20 or 30 routers at that stage. They weren't big backbones, not many routers. And so we didn't really have much issue with this. But as I'll show you later on, this actually is a pretty serious scaling problem. If you think about what a full mesh looks like, how do you fully mesh 1,000 routers? Not very easily. So we'll look at how we get around this issue a bit later. But by default, iBGP's behavior is that it needs to be fully meshed. How we set up our internal BGP peering? Well, it's completely topology independent. This is a good thing. You don't want your iBGP to be dependent on what your network topology looks like. So we've set up every iBGP speaker to speak to every other one. So that's an example there. Router C is not part of this topology, which is actually not a very good example, but it's not part of this particular topology, at least from iBGP point of view. So that's how we generally set up the iBGP, this topology independence. OSPF and ISIS have got a much better idea of how to find your neighboring router than BGP has. BGP by design is generally fairly slowly changing, whereas OSPF and ISIS you can configure to be really, really tolerant of failures in the network. But I've seen many examples, again, of not so much in North America, but certainly in parts of Asia and Africa, where ISPs are running the worst infrastructure you could ever imagine, but they can run a very, very stable iBGP, give a very good experience to the customers, simply because they've set up iBGP properly. And one way they'll actually do all this, we set up the iBGP peering between the loopback interfaces, for example, on the router. A loopback interface is one that will never, ever go down. You can't unplug it. You can't shut it down. Well, you can shut it down, but you can't unplug it. You can't physically remove it from the router. You can't unplug cables from it. So if you set up an iBGP session between loopbacks on the different routers, the iBGP session will really just stay up as long as the router is still functioning. For example, if we didn't run it between loopbacks, if we run iBGP on the point-to-point links between the routers, well, that would work fine too until a link would break. If this link broke, the iBGP session between these two routers would go down. Okay? The iBGP session going down simply means that any customer connected to this router would no longer be able to see any customer connected to that router or any external network. Right? Because this router would still speak iBGP with this one, but this one being an iBGP speaker would not take any prefixes he learns from there and pass them on to here, because you say, well, we should be fully meshed. So he'll have already heard them directly. And if the direct peering is down, you end up really with a discontinuity in your own network. If you set up the iBGP between the loopbacks, right? If you set them up between the loopbacks in the network, this link goes down, OSPF just comes along and says, hey, oh well, direct path to this loopback's gone down, I'll just use this path. Slightly longer, but hey, it's a path that is still available. So OSPF does a very quick reroute, alternative path around this way. The iBGP session probably doesn't even notice. The next hop may change according to, sorry, the OSPF next hop may change, but as far as iBGP is concerned, the neighbor is still this particular loopback there. So this gives you a very, very stable network, even though the actual physical infrastructure may be kind of flaky. So this way you end up with the iBGP session completely independent of the state of your own network topology. Now, let's have a look at BGP attributes. First one I want to look at is the AS path. The AS path is the sequence of autonomous systems a route has traversed. So for example, if AS100 originates a prefix into the routing system, say 180.10/16, they pass it to AS200, 200 passes it to AS300. If we take a look at AS400, we'll see 180.10/16 with that string of numbers behind it. And that string of numbers is the AS path. It's a list of autonomous systems that the announcement has gone through. The first one is, well, who we've heard it from. The second one is who they've heard it from. And the third one is who they've heard it from. And because this one is at the end of the line, it's basically the origin autonomous system. So you can tell from the AS path who originated, or which AS originated the prefix. What we have the AS path for, it's there for loop detection. If AS400's got a connection back to AS100, well, we wouldn't particularly want AS400 to send AS100's prefix back to them. If we did, we could end up going round and round and round until we ran out of memory or something else broke. And it's also very useful for applying policy. Part of the BGP path selection, for example, is to take a look at the AS path. Okay, we prefer a short AS path over a long AS path. It's the same as flying around anywhere, well, within the US. It's better to fly like non-stop than it is to bounce through every single city like the airlines seem to want us to do these days. So BGP does this kind of thing. That's what the AS path is used for. What does it look like with 32-bit AS numbers, given that we're entering a 32-bit AS number world? Well, I've introduced 3 ASs here with 32-bit AS numbers using the 16.16 notation. So we've got AS 1.2 here, and we've got 3.6 there. They're originating prefixes. If we sit in AS400 is sitting in the 16-bit world. They'll see, well, 300, and then 23456, 23456. Remember, 23456 is used to represent 32-bit ASs in the 16-bit AS world. So it'll look like this. So if you look on your router today, you'll probably see ASs with this in the path. If you do a search for this, 23456 in the path, I think you'll see 5 prefixes originated from 23456 style ASs. It's not that somebody's taken it over, it's somebody is now using a 32-bit AS number. If we look on a AS that's sitting in the 32-bit AS space, well, the representation could look like this. It could be 300, and then 1.2, 3.6 as the origins there, and 170.10 is coming from AS 1.2, so 300, 1.2, and 300, 456. What happened there? 150.10? Sorry, I've got this wrong. This should be 400. Okay? 300, 400. So in the 32-bit space, it would end up looking something like that. So there's nothing amazingly different. It's just how we would view it. Notice that the AS path length is always maintained. Right? We don't sort of aggregate all the 2, 3, 4, 5, 6s into one. We keep the length looking the same. Can you use the mic? Or I can repeat the question, whichever.
Does that imply there's no reachability between a 32-bit ASN and another 32-bit ASN if they're traversing a 16-bit ASN?
Okay, does that imply there's no reachability between two 32-bit ASNs if they're traversing a 16-bit ASN? Yes, there is reachability. The AS 4-byte attribute is basically any BGP speaker that doesn't recognize the attribute should just pass it through.
But it just looks like different prefixes, or one ASN advertising different prefixes from different locations instead of consistent ASN.
In the 16-bit world, yeah. So, yeah. Okay, I'll see. Okay, I'm just trying to explain because it's being recorded. Okay, so if you're sitting in the 16-bit world, you have no idea which 32-bit AS number this is from. It just looks like 23456. You need a router that can speak 32-bit ASN to actually see which ASN originated this. There can be an issue with path selection and so forth because you don't know what this is. And I know Jeff Houston and Randy Bush have been doing some testing work to try and prove this. And it's kind of, yeah, convergence will be slowed a little bit, but it's not a disaster. Okay? So it's not optimal, but things still work. They haven't found situations that would break badly yet. So this should generally be all okay. Okay, so I just included this just to let you see, because 32-bit ASNs, they're being handed out by the registries. At least Quagga and OpenBGPD, high-end Cisco iOS, and one of the Juniper Junoses, I think on the E series, has 32-bit ASN. I think a Redback box has 32-bit ASNs as well. So those are the products that have it, and so guys with those devices will be playing with these AS numbers. I don't know if anybody's going to use them in real-life production yet, probably soon, because at the moment you can go to the registry and say, well, if you don't say what you want, you get a 16-bit AS number. If you specify in the comment section of the form saying you want a 32-bit AS number, you get a 32-bit AS number. Okay? In 2009, 1st of January, it swaps around. You get a 32-bit AS number by default, and you have to say in the comments section, I want a 16-bit to get a 16-bit. So the presumption is that we move fully over to 32-bit on 1st of January 2009. 1st of January 2010, you only get a 32-bit. You no longer get a 16-bit. So I don't know how many 16 bits will be left after that, probably a few. Don't know what will happen. That just hasn't been talked about. So I'm putting this in here, and it'll be in future presentations like this, just so that you know that this is one of the coming things you need to be aware of. Okay, so the AS path loop detection, just to show this one. Going back to the slide before the last one, if AS500 connects background to AS100, how does the loop detection actually work? Well, the BGP speaker sitting here, what they do is, he will look for all the BGP announcements coming into his network. He will look for any announcement that has his AS number in there as part of the AS path. If he sees any prefix that has his AS in the AS path, it will be discarded, because it's like, well, it's my AS, so I've already originated this prefix, so I don't need to accept it. So that's part of loop detection. If you didn't have that, this 180.10.16 could just end up being announced round and round and round in circles, okay, as a worst case. So you tend not to want that. You find that some BGP implementations also apply a bit of intelligence at the announcement bit. 500 talking to 100, the speaker here may come along and say, oh, if I'm peering with AS100, then I'm not going to send anything with AS100 in the path to AS100, because, well, it's theirs. They've already got it. So you need to be aware of that as well, that some implementations will actually block that as well, just to aid with the loop detection issue. Okay, so that's the AS path loop detection. I don't mention it in this presentation, but one thing to be aware of, when people are multi-homing, they use something called AS path prepend, which artificially changes or lengthens the AS path, and you do that by inserting your own AS number. If you insert somebody else's AS number when you do the AS path prepend, you block access to that AS. Now, some people do that on purpose, and other people do it by accident. I think there was a presentation a couple of nanogs ago about that kind of, what it was, I don't remember what the title was called now, but it was basically looking for anomalies in the BGP table. And certainly it's work that a friend of mine, Gaurav Upadhyay in Nepal, has been doing. And he's presented it quite a few times now at NANOG in South Asia. It's some of these anomalies that crop up. It came out purely out of some other side research work that he was doing. But you see a lot of instances where people have accidentally inserted the wrong AS number, and then they've come asking, why can't I reach such and such a network? Well, if you hadn't inserted their AS number, then you would have been okay. So this loop detection bit can have a side effect, which some people use on purpose and others are using by accident and end up with things they don't want. So be aware of it. The next attribute is the next hop. Now, the next hop is basically the IP address of the external neighbor. So for eBGP, if we're sitting on router B, the next hop is basically the IP address of the neighboring router, the router you got the announcement from. So the next hop for anything learned from AS200 will be the IP address on this point-to-point link of router A, right there. So we sit on router B, we see the next hop for 150.10.16 is literally the IP address of the neighboring router, router A. B is a BGP speaker. It will take an external prefix, pass it on by iBGP to router C. We sit on router C. The next hop address is exactly the same. So again, this is a default behavior. The next hop address is maintained. So router C has to know how to get to that next hop. And again, this can be the undoing of many newcomers to BGP. They set up BGP all quite nicely, and it's all working, and they're all happy. And then they discover they've got no connectivity, because router C here says, oh, I don't know how to get to that next hop. So by default, people have to ensure that the external point-to-point links are always reachable within their own internal network, which means that you have to put your external point-to-point link into your IGP, so into OSPF or ISIS. So this can catch out a lot of newcomers. And I don't do them here in North America, but I do a lot of BGP routing workshops in many, well, mostly in Asia, Africa, mostly in Asia and Africa, teaching people really how to move their networks away from static routing and RIP and getting on to using OSPF and iBGP and eBGP. And one of the biggest difficulties I tend to come across is understanding this concept of the next hop being the neighboring address. And most implementations these days certainly have this concept of changing the next hop to be the local router. So this next hop self is what is called in Cisco IOS, where you change the external next hop address to being that of just the local router, because this one knows how to get out there, and this one, well, doesn't need to know how to get out there. It knows how to get here, which means you don't need to carry that external point-to-point link around in your IGP. And doing that, changing that from the default behavior actually is quite helpful for a lot of people, because they don't have to remember that one extra step. Okay, so that's the next hop attribute. If we look inside iBGP itself, how the next hop works here, well, if you're running your iBGP fully meshed, as I said, between the loopbacks of all the routers, then the next hop address of all internally learned prefixes, say you've got a customer connecting here to router B, the next hop address would be the loopback interface address of router B. So we look on router A, how to reach the customer, we go to this next hop address. OSPF or ISIS, whatever you use, takes care of how to get to that loopback. So if your infrastructure link breaks on one particular path, your IGP will basically reroute to the alternative path. And so this way, your next hop doesn't need to change. You end up with pretty good network stability. Okay, it's using something called recursive route lookup, which has just disappeared off the end of the screen there. Let me just go and adjust. Oh, it's a projector, okay. Right, it's just disappeared off the edge. It's recursive route lookup. So basically, your iBGP will look up the routing table, which has been generated from OSPF to figure out how to get to the neighbor. OSPF takes care of all the fast reroute stuff, and your iBGP basically ends up being a load carrier, which is what it's really designed to do. Third-party next hop, I'll mention here because if you don't know about it, you can get caught out. For example, if AS201 is peering with, say, well, router B is peering with router A, there's a shared LAN that's shared with AS200. B will send a prefix towards router A. Router A will send the prefix to router C. What happens to the next hop? Well, the next hop is not changed because the next hop is basically on this LAN. 151.1.3 is on the same LAN as 151.1.2 and 151.1.1. So router C will see the next hop of 120.6.8.1 as being router B. The traffic will go directly from C to B rather than C to A to B. The intention there was efficiency, which kind of makes sense. But at internet exchange points, it can be an issue. You can end up peering with people you didn't expect to be peering with. Okay, not directly, but indirectly through one of your other neighbors, if you're not careful. So that can be a bit of an issue. So yes, it's done for efficiency, but it can have a downside, certainly in situations like that. So summary of all that, you need to use the IGP to carry the route to the next hops. IGP is really efficient at handling all these. You've got your fast reroute if any of the links break. We rely on recursive route lookup, so IBGP basically relies on OSPF ISIs to find the next hops. Means that BGP can be unlinked from the physical topology, and that's actually really important. Okay, the next attribute, origin. Conveys the origin of the prefix. Now, this is not like the name of the router or the IP address of the router or anything else to do with the router. It actually conveys I suppose what routing protocol the prefix came from. And as I said, put in red there, it's a historical attribute. It's not used anymore these days. Well, I mean, some people still use it, but it's generally of no use anymore because it was used in the transition from EGP to BGP itself. I mean, EGP almost predates my involvement in the internet. And so it still exists there as one of the BGP attributes. But as I say, nobody really uses it. Although it is actually used in the best path selection process for BGP. The three values, and again, newcomers to this can find it a little bit confusing, the terminology. Because the three values are IGP, EGP, and well, incomplete. Incomplete is self-explanatory. Well, maybe not. None of them are really self-explanatory. IGP here does not mean OSPF. The IGP here means BGP. It means myself, because I'm BGP protocol. The EGP there refers to the old exterior gateway protocol that predated BGP. And incomplete means it's come from somewhere else. So it's been redistributed into BGP from another routing protocol. So it could be a static route or RIP or OSPF or anything. Okay? So those are the three values that you see, IGP, EGP, and incomplete. And as I said, they're generally not used today. I don't find anybody who's using them, apart from people who think it quite amusing to make all the origins EGP, just to be different. So they can appear in the internet routing table with this origin EGP there, and it looks good. So anyway, I haven't really found any real use for it these days. Likewise, the aggregator attribute. I know there's some ISPs who use them, but quite frankly, its only real use is for debugging purposes. Knowing the IP address of the router that generated the aggregate could be useful for some people. I've never really found it that useful because I find these days that ISPs, when they configure their backbone, they tend to generate the aggregate from more than one box. Well, maybe that can be useful for troubleshooting purposes, but so as I say, I don't find this wonderfully useful in my experience, but of course, somebody is welcome to differ, and they probably will. But the aggregator attribute is purely the IP address of the router that originated the aggregate into the BGP system. Now, local preference. This is the first, well, it's probably not. It's not the first really. It's the second really important one. The first really important one was the AS path. This one is really important. Second really important one, local preference. What happens when you've got this? You've got AS100 originating 160.10/16. We're sitting down on router C and AS400, and you say to router C, okay, we need to go to AS100. Which way do we go today? Well, we as human beings, we can look at this and we can express an opinion. Computers and routers aren't really very good at doing the opinion thing. Nobody has really produced routing software that's got fuzzy logic in it yet. That can do kind of, testing this path, testing that path, and do a feeling, maybe hold the finger up in the air and see which way the wind's blowing. Routers can't really do that. So you need to have a complete set of rules. So you need to tell the router which way to send its packet to get from here over to AS100. And that's where the local preference comes in. Okay, so we're hearing the announcement through AS300, the announcement through AS200. We set a preference on the announcement coming in this way from AS300 to 800. We set a preference of 500 in the announcement coming in from AS200. So router C will now see two paths to AS100, one with preference 500, the other one with preference 800. Highest local preference wins, so therefore router C will send all traffic towards AS100 through the B to E link, going around that way. That's what local preference does. It lets you choose how to steer traffic out of your network. Right? It's set on inbound routing announcements, and it lets you steer traffic out of your network. It's actually the most powerful part of the BGP path selection process. You can override anything and everything that anybody else will try and do by just simply setting a local preference and will override any other policy that people try and imply in your network. It's very easy for you to steer traffic out of your network, right? Because you've got the local preference control of doing so. So local preference, it's a non-transitive attribute. You set it on announcements that you hear from external speakers, and it's only visible within inside your own autonomous system. If you've set a local preference on a prefix, and you announce that prefix to another autonomous system, they ignore it. They basically reset the local preference back to the default. Default in, well, certainly in Cisco iOS is 100. They'll set it back to that default. Determines best path for outbound traffic, highest local preference wins. Okay? When you're learning this, you just have to remember it. Why do you just have to remember it? Because we've got MED, which basically works the opposite way to the local preference. Right, we've got MED, we've got this situation, you're announcing an address block from AS201 to AS200. You want to tell AS200 which inbound path to use. Okay, so local preference determined outbound path, MED is used to determine the inbound path. Okay, so by default, you've got router C trying to make a decision. It tosses a coin and sends packets one way. Oh no, routers don't toss coins. So you need to tell it what to do. If we apply an MED on this outbound announcement from router B, say of 1,000, and an MED of 2,000 on the router A's announcement to router C, well, router C will then see two paths, 126.8.1/24, one with 1,000, one with 2,000 MED. Just to be different, lowest MED wins. Okay, so it's highest local preference, lowest MED. Why lowest MED? Probably because in OSPF and ISIS, lowest metric wins. Because in the old days, well, certainly in BGP version 3, we all talked about BGP metrics. I mean, I still talk about BGP metrics, and you find all through these slides, I still refer to BGP metric, because I can't get out of the habit, even though it's meant to be ancient now, because MED came along with BGP version 4. So I still talk about metric. So lowest MED, I suppose it's a little bit like the lowest IGP metric being the winner there as well. So that's the way to remember it. And if you remember that local preference is the opposite to MED, then you remember highest local preference wins. So, oops, what happened? Okay, right, so that's what happens. So we've got lowest MED on this path, so traffic comes in from C to B. So that's how MED works. Summary of it, it's non-transitive attribute, but it works between autonomous systems. If you set an MED outbound on a peering, sure, it'll get to your neighbor, but your neighbor is not going to transit that MED value to any of their neighbors. It's only going to be visible within their AS. Optional attribute, that's actually caused a huge amount of issues. Well, which I'll get to really on the next slide. But optional attributes a huge number of issues. So, user convey the relative preference of entry points, determines best path for inbound traffic, opposite to local preference. It's compared only if paths are from the same autonomous system. Right? So in the previous slide, it was the paths were from the same autonomous system. So it's only compared if paths are from the same AS. The paths are via different AS. By default, MEDs are not compared. Of course, people came along and said, hey, but we need to compare MEDs with paths from different ASs. So, well, in iOS, there's a knob that says always compare MED. So it will always compare the MED and ignore the AS path information. Lowest MED wins. Absence of MED attribute implies MED value of 0. RFC 4271 documents that. RFC 1771 said nothing. And that was the problem. We ended up with metric confusion. It's non-transitive and optional attribute. So we had some implementations send learned MEDs to iBGP peers by default, others don't. Some send MEDs to eBGP peers by default, others do not. So there's that first issue, because it's an optional attribute. Second issue, default metric varies according to the vendor implementation, because RFC 1771 said nothing. It's an optional attribute. Okay, so if you don't send MED and you get you get one path has an MED set, the other path has no MED set, how do we do a comparison? How do you compare something with nothing? I mean, should the nothing be 0 or should the nothing be infinity? So some people said the nothing was 0. Some people said the nothing was infinity, which is, well, 2 to the 32 minus 1, which is good as. And so you set up BGP sessions between different ISPs and their parallel paths and using MEDs. And of course, if you assumed your neighbor was using the same vendor as you, then it would work properly. If your neighbor was using a different vendor from you who had a different idea of MED, well, you would have the best path coming in the wrong way. And I think it was Curtis Willemars a long time ago did a presentation that basically showed the problems they had. I think it was between UUNet and ANSNet. I think it was then. I could be wrong, but I think it was that, many, many years ago, just showing the whole issue surrounding this. And then there's been another, I think it's an informational RFC that basically said MED is a pretty bad idea altogether because of this particular confusion issue. And you find these days that very few service providers will actually honor MEDs that you set. They're much happier using something called the BGP community, which I'll touch on, and which, well, Richard and Tom will be talking more about tomorrow. They're much happier using a BGP community for signaling policies between different autonomous systems. So you'll find these days that MEDs probably aren't used as much as you would expect because of this particular issue, the metric confusion. Okay, so, and it was just purely because RFC 1771 said nothing about what to treat an absence of an MED value. Okay, next one. Next attribute is the BGP community, and that's described in RFC 1997. It's a transitive attribute, and it's an optional attribute. And it's basically a 32-bit integer. And more or less for the same reasons as the 32-bit AS numbers, humans aren't very good at handling numbers once they get bigger than 100,000. Okay? It's too many digits, and you can start jumbling them up and getting them wrong and so forth. So the actual internet representation, so as the Tony Bates and I think it was Anka Chen used in RFC 1998, was something like this, two 16-bit integers, where you put your local AS number as the first 16-bit, colon, another 16-bit integer. So this sort of representation. They'd write it out like this, rather than just a massive number. Okay, it's much, much easier to try and handle. So you find the common format is something like that. So iOS would be BGP community new format because it still supports the old format. Not that either format is new or old, it's just one is per spec, another one is, well, how we write it in the router configuration. Community is used to group destinations. I mean, it's not a collection of routers speaking BGP, it's actually used to group destinations. And the grouping is something you define. You can put different customers in different communities. I've got one or two examples of those a bit later on. Right? You can group your different customers into different communities and do different things based on those. I mean, I've been around long enough. I remember the days before BGP communities, and boy, was our routing policy at UUNet massively complex. It was really, really complex because we didn't have any way of bundling up our different customers in different sort of groups. We just had to maintain pretty massive access list to try and do what we were trying to do. When communities came along, all that disappeared, and we just dumped customers into different memberships, and the policy became very, very simple. So let's just show you how they work. So you've got an ISP here. He's got his backbone. He's got a couple of customers and different ASs. They're announcing an address block 160.10 into router C. They're announcing another one, AS200, 170.10 into router C. With a community, we just drop them into community 300:1. I'm using the convention. My AS number is the first 16-bit integer, and then the second 16-bit integer is just a number. Okay, you make it up. The There are no predefined uses of communities as such. There are 4 reserved ones, but there are no other predefined communities. So I'm saying, okay, :1, those are my customers. So router E sitting here is talking to, I don't know, it could be a transit provider or peer or something, and he's sending all his customer prefixes to AS400. So what he does is he's got his router sitting there, and he's got a filter that says, send all members of community 300:1 over to router F. So it's a very simple filter to set up. How would this happen without communities? Well, without communities, you've got your router C here. You've got to set up a filter. Okay, he's announcing 160.10.16, so I'm going to let 160.10.16 in. And then I've got to go to router E, and I've got to set up a filter that allows 160.10.16 out. And then 170.10.16 comes along. Oh, I've got to set up another filter to allow him in here, and I've got to let a filter to allow him out there. We're talking about the days before being able to refresh a BGP session silently without breaking the link. To change policies in the old days were to shut down the BGP peering and bring it all up again, which I mean you just can't do in the internet today. So this was really painful. I mean, in our case, well, what did we have to do? We added a new customer. We had maintenance periods Tuesdays and Thursdays, 4 a.m. to 7 a.m. I'm sure you're all familiar with things like that. So we got a customer at 9 a.m. on Thursday. That's when he connected, and he wanted internet now. And we said, yep, you'll get internet on Tuesday at 4 a.m. And it's like, okay, we sign up for service, we start paying today, but we don't get connection on Tuesday. What kind of service is this? Well, you know, but this is when we do our maintenance. We're sorry. So I had many spectacular arguments with our salespeople about this particular thing. Shutting down a BGP session with our upstreams at 10 o'clock in the morning was not good, because we're trying to, you know, we actually had service guarantees back in those days. 99.5% availability was ours. I mean, okay, for 94, 95, that was quite something. But that's what we did, and that's what we managed to stick to. But shutting down BGP sessions just to add customers wasn't really an option. When communities came along, our life became simple. We could connect customers anytime, and they got connectivity anytime, because our customers just jumped into our customer community, and they got sent out to our peers automatically, because they were a member of that particular community. So communities are probably one of the best things that ever happened, I think. And the ISPs who are using them for managing their policies within their own network probably realize this. It really makes the management of the network and the customer address space very, very straightforward. Or at least a lot more straightforward. Say you get a peering set up with ISP2, but you don't want to give peering the prefixes that you learned from ISP2 to this transit provider. Sure, you just pop all his prefixes into 300:9. Got an automatic filter. Okay, we're only allowing 300:1 out. 300:9 is not the same community, so it's blocked. If we didn't have communities, we just have to set up more filters to do what we want to try and do. Okay, so the big advantages of these. I'll touch on some communities a bit later on, just to give you some more examples. There are 4 well-known communities. IANA have finally documented them here, so they did that about a couple of years ago. There's a no export community, which basically if the prefix gets tagged with that, it will not be advertised to any eBGP peers. So if you've got a prefix that you don't want to announce to any neighbors, sure, tag it with no export. If you've got a prefix that you don't want your neighbor to announce to anybody else, when you announce it to them, tag it with no export on your external speaking router. And that way you make sure they won't announce it to anybody else. No advertise. Don't advertise this to any BGP peer. You may have learned a prefix on your router, tag it with no advertise. You're not going to advertise it to any BGP speaker at all. The no export subconfederation, that's used within BGP confederations, which I won't really talk about. The no peer one is relatively new, RFC 3765. Nobody I'm aware of implements it, which is quite disappointing, because it was meant to be a community that we didn't have to go to all these nasty router vendors to try and implement, because the community was going to implement it, only the community hasn't. The no peer one is actually pretty handy. It was intended to try and deal with the size of the routing table problem, because people who are trying to do traffic engineering at the moment are saying, ooh, let's chop up my address space into /24s and spray it out and let's see what happens. And which is what most of the world is doing. So So it was meant to be a way of getting the ISPs who are carrying the full routing table not to have to see the local traffic engineering junk coming from the edges of the internet. But it's there, but nobody uses it. So let's look at two examples. The no export community works like this. So if you're trying to load balance links between two different autonomous systems, like that, for example, well, what you do is you announce your aggregate. So I've picked a number here. Aggregate is being announced out from AS100 to 200. And you announce sub-prefixes. That's a standard way of doing this kind of load balancing. You take your address block, divide it into a few pieces. Not into /24s, a few pieces. Divide into a few pieces, and you announce the pieces with no export on your edge routers there. AS200 will see those pieces. So traffic for the first piece goes there, the second goes there, the third goes there, which is fine. But out to the world, router G sees the no export community being set and will automatically drop these prefixes from any outbound announcements. So the world just sees your aggregate transited through your upstream provider. So that's what the no export community is for, and it's pretty handy. A lot of people actually use it for this sort of thing. The no peer community works like this. I hope you can see that okay. So we've got an autonomous system here. He's announcing his address block, and he's announcing sub-prefixes, again with a view of doing load balancing on his multiple external links. So he announces 170.10.16, of course, and he announces sub-prefixes. So router B in this AS will see the aggregate and one sub-prefix. So you maybe get some traffic in this way, some traffic that way, and some traffic round that way, which is the idea of trying to do the load balancing. But you don't want the default free zone to see this traffic engineering small pieces. Okay, you don't want to see the traffic engineering shrapnel. So what happens is he will set no peer community on his sub-prefix. So router B, basically, sees if the no peer community is set, he won't advertise it to any peers. Well, he doesn't have any peers, he's only got customer and he's only got an upstream. Router E's got 2 peers and 1 customer. So he'll hear 170.10.16 and the sub-prefix, but he'll only send the aggregate to his peers. He won't send it to won't send it anywhere else. Okay? So that's the whole idea of the no peer community. I suppose it'd be really nice if there's actually some router configuration can actually handle the no peer community as well. Because the community is not, well, the industry is not going to actually implement it at least the service providers aren't going to use it. So maybe there's a vendor thing that can be done the same as a no export is silently discarded. So you basically set up a BGP session and you just have one keyword that's, okay, this AS is a peer of mine and the rest aren't. If you say AS blah is a peer, then we drop any prefixes with the no peer community set. And that would go a long way to try and make the industry adopt. I know I work for Cisco, and yes, I've asked for this ever since the RFC was published, but anyway, moving swiftly on. Okay, so community is an optional attribute. Some implementations will send communities to iBGP peers by default, which is a good thing to do. Some do not. Some implementations send communities to eBGP peers by default, which I think is a bad thing to do. Some do not. So you need to be aware of that, especially if you're mixing different vendor products in your network, that they don't all behave quite the same way. So if you want to be consistent, make sure they are the same. Being careless can lead to community confusion. The most favorite one that I've come across is, yeah, I'm going to set no export community to my neighbor. Your neighbor doesn't support community, so what happens with the no export? Boom, it disappears when it lands on their router. So you may be sending sub-prefixes which you assume would be no export, but if your peer or your upstream doesn't support communities, then your no export is lost. I mean, certainly in doing my writing report thing and when I was helping the net police activity in 2000 and trying to get people to improve their aggregation, people said, oh yeah, but I'm setting all no export community on all these prefixes. Yeah, but does your upstream provider actually use communities? Oh, do I need to, doesn't it automatically use them? Well, but if they're not supporting communities, your router's going to ignore the attribute, and so on, as I had in the conversation. So be aware of that. If you're going to use communities between you and your neighbor in AS, especially no export, ask them if they actually support communities. And then things might work as you expect. You need to have a consistent community policy within your own network. That can be quite handy too. Don't make assumptions about what your upstreams or your neighbors have with communities. If they publish a website that says these are the communities that we support, it's probably worth actually checking that they support the communities before you just go and blindly use them. Because quite often the people who maintain the website are not the same people who run the network. So there can be a bit of slippage between the two. So it's worth checking. Okay, next. Okay, the question is, what about additive? Can you have many communities per prefix? Yes, you can have well, in theory, you can have as many as you like. I think most implementations set some kind of limit. I think Cisco iOS limit is 32 communities or something. But generally, yes, your prefix can belong to more than one community. Yeah. Okay, microphone echoing somewhere. Okay, I'll carry on and hope it's all right. Right, so the BGP path selection algorithm. So it's basically, why is this the best path? How does BGP figure out what the best path is? It's very difficult to give a generic path selection algorithm because, well, the RFC one is quite simplified because it's obviously trying to be vendor independent, but then each vendor has come along and made its own little tweaks. So rather than trying to present every single one, I've just said, well, look, here's the Cisco one. It'll be very, very similar to whatever other platform you're using. I spared some of the details, the nitty details, but this is the general thing. It is as per the spec, but the one or two extra bits and pieces in as well. So the first one really is, do not consider path if there's no route to the next hop. That's the major one that catches out a lot of people. Don't consider the path if there's no route to the next hop. If you can't reach if your router has no routing table entry for the next hop, we're not going to look at the path. As I said, it's a major newcomer stumbling block, because newcomers, oh yeah, I've got my BGP all set up, got all these prefixes, got all my next hops, but nothing's happening. There's no traffic. What's going on? It's because, well, how is your next hop in your IGP? Is it in the routing table? Sure, BGP will pass on the attribute. That doesn't mean you can actually reach it. So if the next hop is not reachable, we don't even start. Okay, the path is not even considered. This is special to Cisco. Do not consider the iBGP path if you're not synchronized. In the old days, it was kind of important that people synchronize the IGP and the BGP. And I really do mean old days. I don't think anybody in the right mind would try that today. 221,000 prefixes or 222,000 prefixes in the BGP table, and trying to have it synchronized with OSPF? Probably not. So this is not really relevant, but it's worth putting in there because, again, it's another one that catches folks out. The weight I haven't really mentioned. It's not really a BGP attribute. It's not really vendor proprietary either because each implementation actually has a concept like the weight. So I'm not quite sure where to fit it in the scheme of things, but it actually does appear here. The weight is a local preference. So it's a local preference that is local to the router. You set a weight on the router. So if you learn a prefix from a neighbor, you set the weight on it, that weight will override anything else you hear from your network. The weight is used especially in things like if you're going to do a reverse path forwarding check, unicast reverse path forwarding check and so forth. It can be particularly useful for that. So the first real one of the path selection process is the highest local preference. We take the paths, pick the one with the highest local preference. Okay, so the highest local preference wins. So it's first, pretty much. Highest local preference, as I said, overrides everything else. If the local preference values are the same, then we prefer the locally originated route. So if it's been originated locally versus originated somewhere else, then we prefer the locally originated one. Kind of makes sense as well. If not, then we pick the shortest AS path. Now that actually wasn't in the original BGP spec as far as I remember, but pretty much everybody said, well, we need this. This is just complete nonsense. Why jump through 15 hops when it's just my immediate BGP neighbor? So shortest AS path. okay, which generally can make sense. Okay, shortest AS path is the next one. If the AS path lengths are the same, we go on to the next step, lowest origin code. Remember I said origin is more or less historic these days. IGP is more important than EGP, is more important than incomplete. So that allowed us to do the migration from EGP to BGP pretty much. The origin codes are the same. We then look at the lowest MED. MED is only considered if paths are from the same AS. That is the default. But of course, you know, in the internet space, we've added a couple of knobs. This one, BGP always compare MED. We basically ignore the AS path. We compare the MED for all paths to get to that particular destination. Okay, we always compare the MED. This one, BGP deterministic MED. What does this all mean? Well, the BGP spec, again, didn't say what to do if you've got multiple paths to the same destination. Because the router will basically store them in the BGP table in the order that it heard them. Which, well, I mean, if you've got 2 links to your neighboring AS, it's fine. What about ISPs that got 5, 10, 15, 20 links to another AS? How do you handle things then? They spent a week fine-tuning the load balancing. You do maintenance on one link. The link goes down, BGP session goes down, BGP session comes back, link comes back, prefix comes back. Oh, it's in a different position in the table. The best path selection result is different. Okay, so your finely tuned load balancing is now completely different. So that wasn't too handy. So the BGP deterministic MED was, well, okay, in Cisco's case, was a way of ordering the paths deterministically before we do any of the comparison. So the paths are ordered by increasing AS number. So they're always going to be the same order, no matter what maintenance you do on any of the links between the ASs. So you always get the same answer. I mean, when this first became an issue, probably about 7 or 8 years ago, it was a case of BGP's made a mistake. Well, BGP, bugs aside, doesn't generally make mistakes. It's just that the rules didn't cover all particular scenarios. Right? So BGP deterministic MED, well, certainly from my point of view, is more or less a mandatory thing that needs to be configured on the BGP session. I mean, if your implementation just doesn't have this problem, it's not a problem. But if your implementation doesn't have any sort of fixed ordering for the paths that it learns, or it orders them by age or something, then you'll probably need to consider this if you've got multiple links to the same AS. Okay, if the MED is all the same, then we prefer the external path over the internal path. That's the first one of the hot potato routing. You know, hot potato is, if it's too hot to hold, you kind of throw it in the air at somebody else, and they catch it's too hot to catch, so you throw it on. Hot potato, hot coals, whatever you want to call them. If the destination is outside your network, you want to get rid of the traffic as quickly as possible. So that's what this is basically saying. Go out of the network rather than transporting it across my backbone. Okay? So packet lands on your external speaking router, it's going to go out of your network rather than go through an internal path to another external router. And following on from that, one path with the lowest IGP metric to the next hop, which is pretty much get out of the network on the biggest bandwidth available. Okay, biggest internal backbone bandwidth available. Matters especially where backbones have different bandwidth on the internal backbone links. You want to pick the biggest bandwidth, generally. Okay, doing the automatic tree. Okay. Okay. So this one is really, if you're using IGP metric to represent the bandwidth in your backbone, which quite a few people actually do, the lower the metric, the bigger the bandwidth on the link, then this is generally saying biggest bandwidth out of my backbone. If IGP metrics are all the same, we're then starting to get desperate. We're looking at the lowest router ID. Okay, so the lowest router ID on our BGP neighbor. So that's basically an IP address. Most router IDs are generated. If the router IDs are the same, we're then looking at cluster list, which I'll talk about when I get to route reflectors in a bit. Then we really are very desperate. Last one, lowest neighbor IP address. And because we must get a best path out of this. Okay, so those are the 3 pages or 3 parts of the BGP path selection process. Again, when I've given the Cisco version of it, your implementation may have, it'll be in the same order, it maybe have extra pieces, it may have pieces missing, whatever. But this is approximately how it actually works. So as I was saying, in multi-vendor environments, make sure the path selection stood for each brand of equipment, because each vendor's got slightly different implementations, it's got extra steps, extra features, and so forth. So it's worth synchronizing them to make sure they're the same. But yes, it's vendor goes, ooh, this is if I try that, maybe that works better. Who knows? Anyway, let's carry on. So I say each vendor's got slightly different implementations, extra step, extra features. So if you're trying to use dual vendor, multi-vendor environment, whatever, you need to try and synchronize these as much as possible. Otherwise, you can get really weird things happening. Final thing is watch out for possible MED confusion. Probably not really worth even trying to use MEDs these days, simply because of our discredited past. And even though the discredited past is now gone, it's just so many people are like, well, there's not really much point even trying to use them these days. BGP communities are better suited to try and support this. Okay, we've still got 5 minutes, so let's look at the next bit. This is applying policy within BGP. It's just trying to fill in a few of the gaps that I've been talking about before. Why do we want to try and apply policy? Well, network operators rarely just plug in routers and go. I mean, that's what happens at the edge of the network. You buy a router, you plug it in, power it up, drop some configuration into it, and it just works because you've got the one upstream and they handle your policy. You don't need to know about it. But you as the service provider, well, that's a different issue. You need to control who you peer with, who you give transit to, and who you actually get transit from. Right? So it's not just a case of a whole wide open shop. I mean, who you peer with, peering is usually no cost. So you don't want to end up with peering with somebody who could be a customer, for example. This new? Okay, am I still working? Yeah, okay. Well, we're not echoing now, so that's good. You don't want to end up peering with somebody who could be a customer, for example. You don't want to give transit to a peer. Again, it's sort of common errors that newcomers to BGP make. And certainly some BGP implementations, or most BGP implementations, you start them up, they take everything in the here, they send out everything you hear, that's the default, rather than actually going and picking and selecting and what you actually send. So that's where the policy comes in for the external relationships. We've also got what I've called traffic flow control. So efficiently use the scarce infrastructure resources, fancy really for trying to do external link load balancing. You want to try and avoid congestion as much as possible. I know it's never completely possible, but you want to do it as much as possible. So terminology, of course, is traffic engineering. So BGP traffic engineering is where a lot of the policy stuff comes in. That's where it's useful. So the BGP attributes are used for these. That's where the BGP attributes come in. You apply policies, so by setting local preference, setting MEDs, well, not really. Using ASPath, ASPath prepends are quite commonly used. You sometimes see deliberate ASPath poisoning, in other words, inserting other people's ASs into the ASPath so you don't get access to the networks. Use of the BGP community, and that can be used to influence the path selection process. Advertising or filtering prefixes, a common way of applying policy. You can advertise or filter prefixes depending on AS number or indeed the AS path. You may not want to use particular AS paths that are visible in your network. Or you can advertise or filter prefixes depending on community membership or communities that you hear from your customers or your peers. all that type of thing is how you apply policies in BGP. The tools, well, I'm not going to go through a major bit of sort of different router vendor configuration tools, but most of them are implementations that tools that will let you apply, well, manipulate prefixes, filter prefixes, manipulate AS paths, filter on AS paths, handle all the community attributes and so forth. Okay, they've all got tools that let you do that quite nicely. They can also have policy languages of different levels which will let you do various match and set constructs and the different attributes chosen for the BGP routes that you're trying to handle. Okay, so those are all the general policy tools available. It's kind of hard to do a tutorial that covers sort of implementing BGP policies without really getting into vendor-specific ways of doing the configurations. And I haven't really touched on public tools like the IR toolset for quite a long time, which can let you generate router configurations from a kind of standard policy description language. But those are other possibilities for tutorials if any folks here have got experience with those and want to talk 90 minutes about that. Actually, I've got a BGP tools buff, but I don't think that's going to be talking about this exactly. Looking at another few slides before we have the break. BGP, of course, has been extended away from just handling unicast IPv4 address space that it was first designed to handle. And this is all part of a greater BGP capability thing, how to add on bits and pieces, optional bits and pieces to BGP. So the BGP capabilities, that's documented in RFC 2842, it's quite old now. Capability parameters are passed in the BGP open messages. So when you bring up a BGP session, your router will say, hey, can you support this? Can you support that? Or it will say, I support this, I support that. Unknown or unsupported capabilities result in a notification message, which generally shouldn't cause an issue. You just get a notify, cannot handle such and such capability. The various capability codes, so the first 63 are assigned by IANA by IETF consensus. In other words, working group has agreed that we need this capability. 64 to 127 are assigned first come, first served by the IANA, and the last 128 are vendor specific. So the current ones we've got, well, capability 1 is multi-protocol extensions for BGP. The second one is the route refresh capability, which I'm going to talk about after the break as part of the scaling part. Cooperative route filtering, I have no idea where that's got. I probably should have an idea, but I don't know. Multiple routes to destination capability, RFC 3107, but I must admit I don't know who's implemented it. Graceful restart, 4724, I know that has been implemented. Support for 4-octet ASNs, in other words, 32-bit AS numbers for you and me, RFC 4893. 66 is gone, 67 dynamic capability, still internet draft, and multi-session BGP, still internet draft. And that's all there are at the moment. So there's some extra capabilities there. The multi-protocol one is pretty important for, well, any folks doing multicast or VPNs or V6 and so forth, because that's how BGP handles those. Route refresh, as I said, will be after the break. So multi-protocol, not going to go anywhere near that here for this. I mean, this is really the BGP techniques and primer style tutorial. Again, if anybody wants to do a VFIL multicast tutorial or V6 tutorial or V6 multicast for BGP or VPN stuff, program committee will be delighted to hear. As I said, so I've mentioned. So, going to quickly look at some scaling techniques, or at least some scaling issues with BGP. So I indicated there was a slight issue with deploying IBGP, because I remember saying that IBGP speakers had to be fully meshed. In other words, they all have to talk to each other because they only transmit external prefixes with an IBGP and only originate prefixes that they announce. Sorry, that they only announce prefixes that they originate. Which is fine for a small network, but what do you do when you've got 100 routers, 200 routers, 500, and so forth? So how do we actually scale this properly? Implementing new policy without causing flaps and route churning, and generally just keep the network nice and stable. Well, we've got route refresh, got route reflectors. I've got the BGP confederation slides in this, but I'm not going to go through BGP confederations. That's why I've put it in brackets here. It's just so that you have reference materials, so that if you hear about people talking about BGP confederations, it's not something that I've deliberately missed out. It's just I'm not going to talk about it because, well, no new implementation today goes down the confederation path. And I'm also going to look at route flap damping. Somebody may have remembered, well, you may remember in the middle of the 40 giggy, 100 giggy presentation or talk, the network disappeared. Then Randy stood at the microphone and said, read my slide from 2002 or whenever it was, why route flap damping is harmful. So I thought I'd just throw that in for good measure as well. Okay, so route refresh is what I'll look at first, just quickly. Well, before we had route refresh, back in the old days when the internet was a bit of fun and nobody took it seriously, nobody ran businesses too much over it, to implement any policy change, you had to reset the BGP session. Because if you think about it, if you change policy, you're basically changing what you announce to your neighbor or what you accept from your neighbor and what you do with it. BGP only sends updates. But a policy change applies to the entire BGP table that you've heard from your neighbor. So, sure, you can implement a policy and it applies to updates, but it won't apply to anything that you've heard about before. So the only way to do it then was to basically shut down the BGP session, bring it back up again, and then you could apply your new policy that you have wanting to implement. This was fine in 1994 when the internet was a bit of a toy and we only used it for mail and FTP. These days, when people are running multi-million-dollar businesses on it, shutting down a BGP session to implement new policy usually means 5 minutes or more of disruption, usually more. And that doesn't go down well to your multi-million-dollar customers saying, oh yeah, we just shut down because we wanted to tweak something. That's not something they really understand. A hard BGP reset terminates BGP peering, consumes CPU. It severely disrupts connectivity for all networks. In fact, if you cycle a BGP session, you can disappear from the internet. And you can disappear probably for up to or even more than half an hour. So it's really not a good idea to reset a BGP session these days. So this is where the soft BGP peer reset came in, or as it's better known, route refresh. But the BGP peering remains active, and what you actually do is you end up sending a note to your neighboring router saying, hey, just send me everything again. That way you don't cause any disruption to the peering session. A soft reset or route refresh will only impact the prefixes affected by the policy change. So for everybody else, things carry on working as normal. So this is the route refresh capability, RFC 2918. Again, it's been around for quite a long time. Still not default in some implementations, which is really annoying. For most implementations, no configuration is required because it's part of the route refresh capability suite, and it's automatically negotiated when you bring up the BGP session. Doesn't need any extra memory. It's a good thing. It's generally just there. So use it if it's supported. I think pretty much every router these days will support it. I think it was about 2 years ago I saw the last router that didn't support route refresh finally disappear. So you can find out from the BGP status display what capabilities the neighbor actually supports. It's non-disruptive. It's good for the internet. If it's not supported, see if the implementation has a workaround. I mean, in fact, before route refresh worked its way through the IETF, there was certainly Cisco had done something called soft reconfiguration. Okay, if you remember the configuration, something like neighbor blah soft reconfiguration inbound. What that did was it actually stored all the prefixes that the neighbor sent to you prior to applying any policy. So it kept all the prefixes prior to the policy, and then it kept all the changes that were made. So if you wanted to reset your inbound policy, you already had a local copy of everything that was sent to you, which is all fine and good, but it does consume extra memory. And certainly in the early days when memory on routers seemed to be in short supply, people were kind of, well, you know, it consumes another 10 meg or something like that just to store all these transmitted prefixes. So that's why route refresh is actually a lot better. Get away from the memory storage requirements and get your neighbor to actually send you the entire set of updates all over again. So some people still use this soft reconfiguration thing, but I don't really see any use in it unless you're trying to debate policies with your neighbor. Because then it lets you find out what your neighbor actually sent to you before you apply any policies. So sometimes implementation will have a workaround. Only hard reset a BGP peer as a last resort. Consider the impact to be the same as that of a router reboot, because it takes almost as long and it has virtually the same impact on the internet at large. Okay, next scaling thing, route reflectors. Now this is all about how to go about scaling IBGP. 13 routers, we've got 78 IBGP sessions. Basically, a full mesh is an n-squared mesh, give or take. Okay, it's close enough. You want to try and avoid this half n, n-1 mesh. It goes up at n squared. Right? Each router you add goes up at n squared. You've got 1,000 routers in the backbone. You've got nearly 500,000 IBGP sessions, which is quite a lot to try and manage. Now, there were two solutions. When the first ISP backbone fell over, hit the scaling limit of a full mesh network, two solutions were really developed to work around the problem. Confederation actually came first. It was coded up very, very quickly to rescue said ISP's backbone. Anyway, it is actually a very neat solution to that particular problem. I'm not going to go through the slides for it. As you'll see, it's probably a little bit more complex to actually deploy. I see it as having virtually no advantage over the route reflector, which I will describe. Basically, confederation involves dividing your backbone into multiple ASs and then making these multiple ASs all peer with each other and then pretend to the outside world that they're really one big autonomous system. So that came along first. And then a few months later, the route reflector was the other solution that came along. And that was a much simpler solution. It's very, very easy to deploy, and it's actually pretty simple to run as well. How does it work? Well, normal IBGP speaker works like this. External prefixes come in to router B. B will send them to router A and on to router C. Router A will not send any prefix to router C because it's an IBGP speaker. An IBGP speaker does not take prefixes it learns from one IBGP speaker and pass them on to another IBGP speaker. So this is normal IBGP. If we make router A a route reflector, it takes the prefix it learns from router B and sends it on to router C. Okay, so that's the change that we've made. And you look at this and you go, well, why didn't they do this from the start? I have no idea. I mean, it's such a beautiful, simple thing. You specify that particular routers in your backbone are route reflectors, and they will transmit prefixes, IBGP prefixes, onto other IBGP speakers. And that's how we scale the IBGP mesh. So your network, at least from the IBGP point of view, ends up looking like this. Rather than having a full mesh with these 12 routers, you have a concept of the backbone here. So you've got routers A, B, and C are the backbone. They're the route reflectors. And then you've got the client routers sitting around at the edge. So these could be your aggregation routers, for example. So these are all clients of route reflector A. Likewise, these three are clients of B, and these three are clients of C. Right, so you've got A, B, and C route reflectors. They still have the full mesh IBGP with each other because only these guys are the clients. The clients only have an IBGP conversation with their route reflector. So they've only got one neighbor. Right? So even no matter how big your network is, this guy will only have one IBGP neighbor. So this will scale as far as you like. And I've written down the rules here governing route reflectors. So what gets announced where. Basically, a prefix originated by a client, it gets sent to the reflector. Reflector will send it to another client, and it will send it to a non-client. Okay? Prefix originated by, say, one of these routers in the core, it will get sent to router A, obviously because router A is just a normal IBGP neighbor. Because this is a reflector, it takes the prefix, sends it on to a client. Okay, so it'll send it on to a client. A will not take the prefix from B and send it to C. It won't do that. It just because C assumes that it's going to have a BGP session with router B, or at least A assumes that B is going to talk to C, because you've got the standard full mesh there. Okay, so this is beautifully simple. RFC 4456 is an updated RFC for describing how the route reflectors work. Notice that you can fully mesh the clients if you want to. So some people do this, especially when the clients are over a distributed infrastructure. A polite way of saying you've got one client in each city in the country or something, which some ISPs seem to want to do. Or you can just run it like this, which is what most folks tend to do. You tend to set up a route reflector client relationship within a point of presence. So maybe your two core routers are the route reflectors, and all the other routers in the POP are the clients. That's typically what people do. I'm not going to go into the rights and wrongs of deployments too much here, but you find in some parts of the world that ISP will set up the route reflector in one city. And they have one router as a route reflector, and it's in one city. And then all other routers in the entire backbone are clients. And then they wonder why they have severe scaling problems. Okay, they end up with an n times scaling problem rather than doing it more tidily like this. And of course, if that one router breaks, you lose your entire backbone. Rather than this way, if one router breaks, well, you kind of just lose the POP. So the topology, you divide the backbone into multiple clusters. This is the way to do it. Generally follow the backbone point of presence model. At least one route reflector and a few clients per cluster. Fully mesh the route reflectors. Clients can be fully meshed as well, but generally people don't bother. Don't touch OSPF or ISIS. Okay? Don't touch your interior routing protocol. Some people go down the path, oh, well, I've got to redesign OSPF. You don't have to. The beauty of having OSPF in your backbone, or indeed ISIS, is that the route reflector client model sits nicely on top of how you've deployed the IGP. So you've got your backbone areas and your point of presence areas. Just build your route reflectors to sit exactly on top of that. Two new attributes is the originator ID, so it's basically the router ID of the originator of the route into the local AS. So the route reflector will create that. And you've got the cluster list attribute. It's a bit like the AS path, but it records the router IDs of the route reflectors that the prefix announcement has gone through. And that's actually used the same way as the AS path is. So it's a cluster list attribute. And each route reflector that the prefix goes through will add its own router ID to the cluster list. Best to set the cluster ID from the router ID. I mean, iOS does this automatically, which is nice. I know other implementations don't do this, which is probably a bit more painful. Router ID set from the address of the loopback interface in iOS. Other people may have come up with some other strategy. I know some ISPs do. They've come up with their own cluster ID assignment strategy, but it needs to be well documented. Don't store it up in here, because you probably can't remember where you've stored things, or what numbers are, what numbers have been used. And when you get a clashing cluster ID in your backbone on opposite ends of the network, it can be pretty tough to troubleshoot that one. Certainly when you've been involved in troubleshooting that problem, you learn pretty quickly that this is the best thing to do. Trying to come up with your own cluster ID strategy, while it works fine, can be a bit challenging when it comes to the troubleshooting. Okay, controversy. Multiple route reflectors can be configured in the same cluster, but this is not advised. Why not? How do you get your redundancy then? Well, a router can actually be a client of route reflectors in different clusters. And what you find these days that most ISPs will have two route reflectors sitting on top of each other in the same cluster. I mean, most points of presence have two core routers, and then you've got all the other distribution aggregation, whatever, in the POP. So sure, one core router is in one cluster, the other core router is in another cluster, and all the clients are just members of two clusters. You get your redundancy that way without running into any of the real big problems you have with this cluster ID. The reason I'm pretty strong about this is I've spent too much time troubleshooting national networks, national-sized networks, huge national-sized networks, where they've got one route reflector in one city, the other route reflector in the other city, in the same cluster because they've got the same cluster ID, they've got routers in between, and then they don't understand why, when the network breaks, something goes seriously wrong. Oh, but that's what it says in the book. Well, whose book? What book? Oh, well, documentation on the website. Well, yes, no, documentation is written by people who wrote the code, not necessarily written by the people who are running networks. In the real world, people don't do this, and it's a hard, persuasive thing to say the books are wrong, the internet is doing this. So this is generally what is pretty strongly encouraged advice. Right? Rather have two route reflectors in two different clusters. It ends up looking something like this if you're looking at the general mesh. Your point of presence here, your first cluster is there. These are the two core routers. Your second cluster is here. They're overlaid. Even if one core router disappears, these routers will still get the IBGP information from the other one. I mean, it's just a means of distributing IBGP prefixes. Why build complexity into the network by having these two routers having the same cluster ID? Okay, it just builds in complexity. And yeah, sure, the full mesh and the backbone looks a bit messy like that, but it's not half the scaling issue that you would have had with a general full mesh. So the route reflector solves IBGP scaling problem. There's no real known limit. You can nest these as deep as you want. I know people have nested maybe 2 or 3 deep maximum. There's not really much need beyond that. Doesn't affect packet forwarding. Packet forwarding does not follow the IBGP mesh. IBGP mesh is simply there to distribute prefixes. Normal BGP speakers coexist. This was an issue back in 96, 97 when the route reflector was new. These days, well, I think every BGP implementation can do route reflector, so it's no issue. Use multiple reflectors for redundancy in multiple clusters. Very easy migration, and as I said, multiple layers. Where to place them? Always follow the physical topology. It's just all the scars from having to troubleshoot networks that didn't follow that rule. That is why I increase the emphasis every few years with that, so it's in red now. Always follow the physical topology. Trying to run a route reflector cluster over links that run through other routers that don't belong to the cluster, it just gets too messy. Typical ISP network, as I said, got 2 core routers. They are the route reflectors for the POP. You've got 2 overlaid clusters. Core routers are part of the full mesh. If the core mesh becomes too big, so it's more than 50 or 60 routers, we'll consider subdividing that. When you're migrating, configure 1 cluster pair at a time. Eliminate redundant IBGP sessions. So you can set up the cluster, set up the relationship between the reflector and the client. Once that's running, just strip out the redundant sessions, and you're done. When we migrated our network in the UK, about 50 routers at the time, in that one, well, it was a 3-hour maintenance slot. We did it in 2 hours. I would never, ever recommend anybody else to do that, but we were bold and foolish in those days, and we did. And it just worked. Nobody noticed. You know, it was that simple. So something like this. Migrate a small part of the network at a time. Migrate it, see how it works. Once you're happy with it, go and move another bit. If you're starting off a new network, or you're going to deploy BGP for the first time, start with route reflectors. You may as well. Every time I prepare these tutorial slides, I always think, now, should I just start from the beginning and just teach route reflectors as the way of doing IBGP? Then I think, well, maybe better not, because some people may think they never need it. And so they want to start off with a full mesh, and we don't want the mistakes. So that's why I still say, right, BGP by default is full mesh, but really the way you want to deploy it is do the route reflector from day one. Most of the ISPs that I've touched and deployed, help them deploy BGP from the start. They start off with route reflectors, even if they've only got 4 routers in the network. The thing is, they don't need to go and change. You've got 4 routers and leave them full mesh. Sure, it'll work until you've got 20 routers. Then you've got to come along and migrate everything over to the route reflector to get better scalability. If you start off with route reflector from day one, then sure, once you've gone up to 10, then you're adding another route reflector, maybe a different cluster. It just scales without you having to redesign stuff. What is it saying I heard a few weeks ago? The clever sysadmin is the lazy sysadmin? Or maybe I got that the wrong way around. But it's something like that. And if you can design your whole network and your whole operation so you don't have to do everything, then you've done it really well. Right? Design yourself out of a job, or managers, delegate yourself out of a job. That was what my manager at UNet always told me. Delegate yourself out of a job, then you're the perfect manager. Right, okay, and what do I do then? Okay, but you see what I mean. Try and make sure your network deployment is going to be nice, simple, scalable, so you don't have to go and redesign it every 6 months. So as I said, confederation slides are here. I'm not going to go through them. They're there for information. Happy reading. Well, comparison. Well, you can tell from these. I mean, okay, the confederation folks will probably argue these slides, but well, I've used route reflectors from day one, and I've tried to use confederation, and I find them mind-bogglingly confusing and hard work compared with the route reflectors. So it reflects my bias. Yeah, one other point about confederation, which I accept, it can ease the absorbing of other ISPs into your ISP. So if one ISP buys another, because you simply just import their autonomous system entirely into part of your confederation. Sure. So if you're on a spending spree buying up lots of little ISPs, then this probably makes sense. If not, just start with route reflectors. Okay, flap damping. Can I just have a bite of ice cream before it runs onto the tablecloth? This was a bad idea. But I went out there just to get a refresh of tea, and people said, there's ice cream, there's some left, go and get some before it all goes. So anyway, route flap damping. So route flap damping was this wonderful, amazing network internet rescuing thing in the mid-90s. It was the best thing that ever happened because it made all networks stable. And then, well, I think it really worked. It was really work that Craig Labovitz and Abba Ahuja were doing, like 98, 99, 2000. And they started saying, wait a minute, this route flap damping stuff is it's doing weird stuff to the network. And they found issues like it was making the network converge a lot more slowly than they would have expected. What was happening? So for many years, it was strongly recommended. I mean, Cisco documentation said it. I stood up on this stage and said things like that as well. You've got to use route flap damping because it's the best thing ever happened for your network. I think the first BGP tutorial I did here said that. And ever since then, I've repented. Because it actually seems to cause far greater network instability than it actually cures. First, the theory. Okay, route flap is basically going up and down of a path or change in an attribute. Actually, the change in an attribute is the thing that most people forget. They think, oh, just a withdraw and then announce. That's a flap. Yeah, but if the attribute changes, that's also counted as a flap. And you get lots and lots of attribute changes, especially since BGP communities arrived, for example. Or when a prefix flaps, you get an AS path change, and that's considered a flap. Anyway, so the idea is that it ripples through the entire internet, it wastes CPU. And certainly in the early mid-90s, people were still connecting with dial-up. So they're connecting by dial-up to get their mail. They announced their class C or /24, as it then became. Announce it for 3 minutes, then it hung up, and then 3 minutes later they'd dial up again, get any more email. You know how it all works, dial on demand. So we're getting all these /24 announcements appearing on the internet. And it was really causing a serious amount of CPU. I mean, I remember back in those days, my AGSs, probably about 20% of the CPU was purely handling BGP updates. It was quite a scary number, considering the numbers we see today. 20% just handling BGP updates. And of course, if you had any event on the internet, it would get even worse. The CPU would shoot up to 100% for several minutes. Not good. So flap damping came along. IRC 2439 basically described it. You wanted fast convergence for normal route changes. So if you announce a prefix, sure, you want the network to converge. But if you're going to bounce a prefix all the time, you want it to be ignored. Use history to predict the future. I know it's a novel concept, but that was pretty important. We want to suppress oscillating routes and advertise stable ones. The way it works, we added a penalty for each flap. So iOS adds a penalty of 1,000. A change in attribute also gets a penalty. In that case, it was 500. This was often forgotten. In fact, Cisco never documented it until about 4 years ago, 5 years ago or something, which was a bit of a shame because a lot of people saying, this prefix hasn't flapped, how come there's a penalty? So that's one to watch. We exponentially decay the penalty. So half-life determines the decay rate, and you can change the half-life to what you want. Penalty goes above a suppress limit. We don't advertise it to external neighbors. Goes below a reuse limit, then we can re-advertise it. So once it goes below a reuse limit, then of course the flapping must have stopped. Picture explains all that. So we get all the flaps. The penalty goes above suppress. The prefix is then suppressed, flap, 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 somebody fixes the problem. Then we get exponential decay until we go below a reuse limit, and then the prefix is re-advertised. That's basically how it works. So in this case, which is talking about the Cisco defaults, 2 flaps and you're gone. Well, 3 flaps and you're gone. And you can be gone for a long time. 30 minutes, an hour, again, depending on the implementation. Be 3 flaps and you're gone for quite a long time. How do you explain that to a customer? So it was a pretty severe hit. If you flapped your network, you could be guaranteed that you'd disappear from many parts of the internet. And it's not something you can log in somewhere else and fix, or you can go complaining to somebody to go and fix. You just have to wait for the timeout to expire. It only applies to inbound announcements from eBGP peers. And it only applies to the path that actually flaps. Okay? So if you've got a stable path, you don't apply any penalty to that particular one. It's only applied to external BGP. It's amazing we still get people coming along and say, hey, we need flap damping for iBGP. And I'm like, what? Why? If your internal BGP is flapping, what on earth is wrong with your infrastructure? I mean, you should be using the model of iBGP between loopbacks, and then you've got OSPF or ISI sitting underneath to control the reachability. If your iBGP is flapping, there's something seriously wrong. Oh, well, but my customer link is going up and down. Well, sure, have the link to your customer set up such that their prefix always appears in iBGP. But anyway, there's still people who are demanding this as a requirement. Why would you want to flap dampen your own network? It doesn't make any sense. Well, to me, it doesn't make any sense. And I've lived on both sides of the fence, and I just don't understand why. So you can configure, you can control all these things quite easily. These are the knobs you can switch. There's policy you can implement. So the first implementations on the internet by about 1995, sometime around about then. And of course, well, I think Cisco was the first implementation. It was a case of, well, what numbers do we use for the half-life? What numbers do we use for the suppressor limit, reuse limit? How many flaps? No idea, no experience. So we picked some numbers. Unfortunately, we found out very quickly from the experience that these numbers were no good. They were far too severe. So the RIPE routing working group, which is a working group of the, well, RIPE, which is the, how do you describe RIPE? It's the, I suppose it's almost equivalent to NANOG, but it's closely aligned to the RIPE NCC, which is a registry. They have working groups. One of those is the routing one. And I mean, I was involved in that as well as some of my team at UUNet then. And, well, we saw that the flap damping values, the standard ones, were too severe. So we came up with recommendations documented like RIPE 178, then replaced by RIPE 210, and replaced by 229, that suggested flap damping values. And we came up with configurations for Cisco and Juniper and Foundry and a few others, saying, well, this is the configuration you should drop in your router. Don't do any flap damping on the actual root name servers. So the actual root name servers, you don't want to flap dampen those. And then we had long arguments about, oh, well, but the CCTLD should be in there as well because the countries don't want to be cut off. Well, but anyway, so we don't want to get into that argument because then all the other critical infrastructure came crawling out of the woodwork, and then operators became critical infrastructure, etc. So it all got pretty messy, as you can see if you look in RIPE 229. So we did all that to try and at least get some sanity into it all. But many ISPs simply switched on the vendor's default values without thinking because they got the Cisco or the Juniper configuration cookbooks, and Cisco and Juniper said this, and so they did that, and that was it. And then we came along and said, oh, well, you should do this. Oh, but my vendor says this should be the configuration. And of course, they're right, aren't they? So, and I still find it, many parts of the world, the ISPs are still switching on the default without thinking. So this is, let me see, we've got route flap damping exacerbates internet routing convergence. Well, that's Morley Mao's work carried on from what Abba and Craig were doing. What's the sound of one route flapping? Tim Griffin, AT&T, did that in 2002, and I think Randy was involved in that also. Happy Packets, which was, well, it ended up being related work that Randy and friends were doing. He was looking at trying to get packets through the internet and how happy would they be, like what's the likelihood they'd actually get through to the other end?
and then you discovered all sorts of nastiness that flap damping was causing. So there's lots of badness. 2002 was really when it all came to a head. Problems: one-path flaps. BGP speaker picks the next best path, announces to all peers, flap counters incremented. Those peers see a change in best path. Flap counters incremented because the attribute has changed. After a few hops, peers see multiple changes simply caused by a single flap. I didn't really believe this. It was as bad as it was. And I was helping ISPs in South Asia doing multi-homing. We would announce a /24 to do traffic engineering. So we signed out a 24, and we saw that it didn't really work so well, so we withdrew it. I went to, route views just to pick a place, and I saw the prefix it flapped 10 times. And I went, wow, that's pretty impressive. For one announcement and a withdrawal, it flaps 10 times. How is this possible? And then I started reading some of these papers, and then I saw it was very possible. So it's not good. And of course, Cisco defaults, Juniper defaults, flap 3 times, gone. So flapping it 10 times is really not such a good idea, just for a single announcement. Second problem, different BGP implementations have different transit time for prefixes. Some hold on to it before they advertise. This is the minimum right advertising thing. Now, we've had discussion at the right meetings, and I think we've had the discussion at NANOG a few years ago. Right, so some folks hold on to it. So implementations, others advertise immediately. So you end up with this race to the finish line. So prefix transits through all Cisco network, it takes a certain amount of time. It transits through all Juniper network, it takes another amount of time, and they're different. And so as soon as you start mixing these two implementations together, you get this complete race. So AS path is always changing. And so you get the flap counter incrementing, prefixes being suppressed, simply because you've got this different transit time. Bad, 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 bad. Solution: do not use right flap damping as it stands at the moment. Okay, we need the vendors to actually change this, or we need the standards folks to actually figure out something a lot better to do. I mean, the flap damping itself is a nice idea, but the way it's been implemented today is really badly broken for the internet. Okay, it will impair access to your network and to the internet in general. How do you explain to a customer that, oh, well, you bounce a peering, and suddenly you've got no network connectivity for the next hour or so? So actually, we've tried to document some of the issues in RIPE 378. So these are the same folks who were involved in the original flap damping is a good thing. So RIPE 378 says flap damping is a bad thing, and here is why. So if you're using it now, I would seriously consider switching it off. Okay, before this runs. Right, using communities. So these are just some examples which I'll fly through very, very quickly. As I said, there's a BGP communities tutorial tomorrow, Richard Steenbergen and Tom Scholl, so go to that. I'm not trying to steal anything of what they're doing. This is just a quick intro. I consider the use of BGP communities another scaling technique. It's a very, very powerful, important scaling technique. You basically end up grouping prefixes into different classes or communities within the network. Each community can be used to imply a different thing and has a different result. So let's have a look. You generally set them in 2 places. At the edge of the network for the customer. So the customer edge, you drop your customers into different communities depending on maybe what services they buy or services you want to give them. Or at the internet edge, depending on load sharing or traffic engineering requirements of the local ISP, or maybe what your customers want. So I've got 2 examples. So this is the customer edge. You've got 3 connections to the internet. Maybe you connect to an internet exchange point. So that gets you all your local peers. Maybe you've got a private peering with an ISP who's not at the exchange point. And you've got your transit provider who gives you visibility to the entire internet. And your customers have the option of purchasing combinations of the above connections. I'm not making this example up because this is an example that was dropped on me after I went away on holiday. And sales, of course, had generated this brand new service when I wasn't there to provide technical input. And when I came back, it was, Philip, we need to deploy this tomorrow because that's when the customer gets service. And it's like, yeah, okay. So we ended up with something that was like that. Basically, folks got access to the links, which was the London exchange point. Private peer, I forget who our private peer was at the time. I think it was eBone or somebody, and of course a transit provider, which was UNet's US backbone. So we had to set all this up and give customers different access to different bits, because some customers we didn't give access to the links because, etc. So, for example, community assignments could be like this. For the exchange point connection, we drop them into this community. For the private peering connection, we drop them into that one. Then any BGP session with the exchange point, we announce just community 100:2100. For the peering with the private peer, we announce just community 100:2200. Customers who buy the exchange point only service are dropped into this community. Customers who buy connecting to the peer are dropped into that community. If they buy both, they're dropped into both communities. Customers who want the internet get everything. Okay, so no community at all. This is how we did it. I mean, the variations on this theme. And it was very, very simple. At the edge of a router or BGP sessions, we simply announce prefixes depending on those communities. Simple. I don't think this gives much help. Okay, so the customer edge means that you've got, example means you've got no need to alter the filters at the network border when you add a new customer. You simply drop them into a community. The scalability for us meant that we could basically delegate the installation of new customers and the configuration of our edge routers to a team who couldn't really tell the front of the router from the back. Because we basically had the tools that produced configuration. They could load that into the router and it would just work. The BGP would just work. The prefixes would just get announced, and at least my engineering team no longer had to be involved in setting up of new customers. So it made things so simple compared with what we had to do before. Before, when a new customer connected and had their own address space, okay, we'd set up filters on the aggregation router. We then had to go to all the border routers and change the filters there, and depending on whether route refresh was available, where the maintenance slot was, changing all those filters. It was a real pain. At the internet edge, you maybe have 4 types of peers. You could peer with your customer, exchange point, private peer, transit provider. Again, you can classify all the prefixes. So again, I've just given an example. I'm going quickly because I'm way behind, but these are just some of the examples you can have a look at. Again, what some folks are doing. I imagine these will be covered a bit more tomorrow. So we can drop them into, say, well, customer prefixes, maybe 103,000. The exchange point prefixes, you drop into this one. The private P, you drop into that one. So if a customer buys local connectivity, gets this prefix. Customer who buys local and exchange points gets these, and so forth. Customer wants the internet, well, give them the default route. If they want 222,000 prefixes, charge money for it. Why not? Costs you a lot of money to actually carry 220,000 prefixes in your backbone, so why not charge your customers if they want that? So it means you don't need to create customized filters. This is a good thing. Remember, make the network operation simple. So these are the 2 examples I want to look at. So I've got some ISP examples here so you get a better idea. Some ISPs list this public policy and internet routing registry, so the IRR. Other ISPs put them onto the website. So what I've done, I've gone to some websites and I've gone to some internet routing registries and had a look. So I've taken Sprint. So if you look in Sprint, this is their web page, sprintlink.net/policy/bgp.html. I think that's wrong because it's now this one up there, but whatever. Actually, I think this still goes to there. And so they've described on their BGP page what communities they support. So if you send them, it's probably hard to see at the back, or even hard to see at the front. If you send them community 65,000:XXX, where XXX is one of these autonomous systems here, it says, do not advertise to ASXXX. Okay? Right, so if you don't want your prefix advertised to AS701 by Sprint, you attach community 65,000:701 when you announce your prefix to Sprint. Do these work? Well, yes, I've got access to a few customers who get transferred from Sprint, and yes, these seem to work. Okay? So this is a sort of labor-saving thing that they've set up to try and do. So I think these are pretty neat. These are really useful ones. If you look at the entire list, they're really useful. What about, okay, AAPT. I think there are these. It used to be connect.com.au in Australia. I don't know if these still work because I don't really have anything that's got access to the network, but their routing registry says this. you send them, say, 2764:4, they will lower the local preference by 15 on your prefix. So maybe if you multi-home between these guys and somebody else in Australia, you can make this the backup path by sending community 2764:4. Okay? Or if you multi-home to them, you can maybe set one community 2764:4 and leave the other one alone. You've got your replacement for an NED, right? You send a community and it lowers the local preference. It does the same thing as NEDs, right? So this is actually what people do as a workaround for NEDs these days. They send a community that their upstream supports and it has the same impact. So that's one example. Verizon Business in Europe, now that they finally changed the name to Verizon Business Europe. VisB, I think it's VisB. I have to ask Chris about that. But anyway, so 702.80, set local preference 80 with an AS702. Okay, so again, useful for multi-homing. Or you send them 702:120, set local preference to 120. Okay, so again, set high local preference. So that makes them preferred path for traffic from them to you, and so on. Got some more there. BT Ignite. This is one of the most comprehensive community lists around. I mean, they based all this on work that Tiskelly did many, many years ago. Tiskelly's one seems to have completely vanished, but BT Ignite have taken the list and seems to have implemented it on their network. Again, you look up the routing registry, you'll see this at the bottom of the OTNAM, AS5400. They've got something like this. So for example, if you send community 5400:1000, they will not announce your prefix to all their peers and transits. Okay? Again, really, really useful for signaling to your upstream what to do. And so there are the current transits, and there's various you can do, and all pretty handy. Carrier 1, another example, not going to go through it. Level 3, a really, really complex example. Stuart Bamford is wandering around outside somewhere. If you're interested in these, go and ask him about them, because I don't know, I think this was more exercise in complexity rather than, if you have a look at the complete list, they're really, really complex, and I'm not sure really who uses them. There are obviously the standard ones here, setting local preferences to different values for multi-homing purposes. Okay, so I want to get to the main bit in the last 3/4 of an hour, which is all about deploying BGP in a service provider network. Oh, it's all gone. Okay. It's a hotel, they can clean it. Sorry. Edit that out of the recording. Right. So we've learned all about BGP, at least at non-beginner level. How do we actually go about using it on our network? So I want to recap some important points. Really looking at the role of IGPs and IBGP, because that's pretty important. There's still many people, many parts who can't distinguish between the two, which is unfortunate. Aggregation is my current hobby horse and bugbear. Like anybody who really, well, if you're on the NANOG list, okay, I don't post it very much, but every week I post my routing table report, and I've did the lightning talk last NANOG about the aggregation chaos we're heading into. As the internet's deaggregating like crazy at the moment. Have a look at that. We'll have a look at how you go about receiving prefixes. It's not just a case of open the floodgates and figure out and let the routers work it out. And then we'll have a look at some configuration tips, and I'll try and do all that before 5:30. So, role of IGP and IBGP. Internal routing protocol. Examples are OSPF and IS. There are no others. RIP stands for rest in peace. You should not be using it in ISP backbone. There's still people who think that RIP is perfectly acceptable. No, it's not. Routing protocols, IGPs like OSPF and ISRs are used for carrying infrastructure addresses. They are how your routers work out how to get to each other. That is all they're used for. They're not used for carrying internet prefixes or your customers. Yes, you can try put your customers in there. It'll work when you've got the first 50 or 100. Once you've got to the 50,000th, it might not work so well. So really don't go there from the start. I have this discussion with many ISPs again, more in the emerging internet. Oh, well, but we can do it now because it works. Sure, it works. But when you go to a great big network, it's not going to work. Oh, well, but we'll change it when the time comes. Yeah, right. Everybody says that. Nobody has time. Once you start running a big network, you have no time. Your days expand to 24 hours a week. You don't have time to do a major migration. Design goal for an IGP is to minimize the number of prefixes, so you get best scalability and rapid convergence. 15,000 prefixes in OSPF, well, sure, you can throw the fastest processor at it and you might get the network to converge in a minute or two, but that's not the point. Bolt a bigger turbocharger onto your car, sure, it'll go faster, but it's still not going to win any, well, it's Formula One for me, I think, what's the Indy here in the US, right? You're not going to take your regular street car and win any of these high-spec races. So don't try and make OSPF do things it wasn't meant to do. BGP, we've seen the slide before. There are two BGPs, internal BGP inside your backbone, external BGP for outside. They are not the same routing protocol. They do different things. Do not take your iBGP and spray it out into the internet. Lots of people seem to do that. It is the current fashion. They are different. Like this. We've seen the picture before. So do not distribute BGP into OSPF. OSPF will not thank you for it. Sure, you can get PC and put Quagga onto it, and yeah, you can do it. But in real life, it doesn't work. Okay? That's why you don't see car manufacturers produce all these custom hot rods that people like creating when they're 20-something. Don't distribute IGP routes into BGP. OSPF, dumping it into BGP, they do different things. OSPF is rapidly changing. BGP will probably melt down if it tried to handle all the OSPF changes. And don't put customer prefixes into OSPF. All this, it just will not scale. Right. What you want to do is use iBGP to carry your customer prefixes. The vendors all quite happily say, yeah, my implementation is quite happy carrying 2 million prefixes or whatever. Okay, the size of BGP table in the routers these days does not matter. Okay, the size does not matter. They're quite happy to throw memory into it, into the processors, into the line cards. ISPs seem to be quite happy to pay for endless amounts of memory to carry 220,000 prefixes, so that's not really the problem these days. What you do, point a static route to the customer interface, put the network into the BGP process, ensure that the implementation options are used so that the prefix always remains in iBGP, regardless of the state of the interface. So if your customer link flaps up and down, you don't want your iBGP flapping up and down so that you don't have to send your procurement people to the vendor saying, hey, we want iBGP flap damping. Okay, the options are there. Okay, aggregation. What does aggregation mean? It means announcing the address block received from the registry to other ASs connected to your network. When you get a address block from the registry, they give you an address block. They do not give you 32 Class Cs. Class Cs disappeared in 1994. People are still using them. People still talk about them today, which is a bit puzzling because they're now 13 years old officially. 13 years historic even. So aggregation simply means taking the address block that you've got and announcing it to the world. You can announce sub-prefixes of this aggregate, obviously internally in your network because you're not going to give your whole address block to one customer. And you can announce sub-prefixes to other autonomous systems to aid with homing. But the sub-prefixes you announce are not necessarily the same ones you give to your customers. I'm deliberately having the separation between external BGP and internal BGP. Class Cs do not exist, nor do Class Bs, nor do Class As. They're all prefix lengths of different sizes these days. Unfortunately, more than 50% of the internet routing table is now /24s. Oops, Class Cs. Oh, did I mean /24s? I have no idea. But that's what people are thinking about today. And if you're on the NANOG mailing list, you see the whole discussion about IPv6 and what's the smallest acceptable. Everybody's thinking of /48s in IPv6. Think how many /48s you get in V6 land. People are thinking the wrong thing. Address blocks should be announced to the internet as an aggregate. Sub-prefixes should not be announced to internet unless special circumstances. More later being hopefully the next NANOG if my multi-homing tutorial is accepted. Otherwise, later will be some other time. Aggregates should be generated internally. Don't generate the aggregate on the edge of your network, on your border router. Why not? Well, if your router is in one point of presence, it doesn't matter. If your border router is sitting somewhere far away on a single piece of wire back to your backbone, what happens when the piece of wire gets cut? Well, your router over there is still announcing its aggregate. You get your backup, And it goes round to over this part of the world. This part of the world sends traffic back. Where does it go? It goes to your router announcing the aggregate because it's the shortest path. What does your router announcing aggregate do? He goes, ooh, best path for this is, boom, null. Okay, so you end up cutting yourself off. So this is really important. Generate the aggregate internal and not on the border routers. That's a general good practice thing. ISPs who don't want aggregate are held in poor regard by community. I should take out that slide because I kind of always laugh. I mean, out that bullet, because I kind of always laugh when I say that. I think this was probably true 10 years ago. I'm not so sure how it's true now. And certainly in this part of the world, it's still reasonably true. And when I go to the more emerging parts of the internet and say the same thing, people go, really? Who? And it's like, well, most of the ISPs in Europe and North America. Do they? Yeah. Oh, they never tell us. So it's this whole kind of thing. So it depends where you are. Registries publish the minimum allocation size, which can be, it's generally around about a 21 these days. Some are 22. There are over 117,000/24s. I wonder where they came from. No, they did not come from the former Class C space, or at least the former bit of Class C space that was actually used, 192. No, they didn't come from there. There are people going, ooh, I need to multi-home. How do I multi-home? Ah, we'll use a shotgun. That works. Here's an example that I see all so often. You may find this hard to believe, but a lot of people think this way. We've got our customer. Customer's getting address space from our address block. When our customer connects, we announce our customer address block out to the internet. When our customer does not connect, we don't announce it. When we don't have customer using this address space, we don't announce it. So they basically leak the IBGP out to the internet. And we think this is perfectly okay. There's a whole continent that's doing this, and well, subcontinent that's doing this, and doesn't think it's a bad thing. And when I try and change it, I'm somehow the bad person. Well, what's the issue? And this is why the internet in that particular part of the world is really pretty poor. Customer link goes down. The /23 network becomes unreachable. Well, of course. It's withdrawn from IBGP. Well, okay, that's where one of the IBGP flat dumping things comes from. The ISP doesn't aggregate its /19 network or whatever it was at the border. So the /23 withdrawal goes out into the internet through the 22,500 autonomous systems. How many routers there? No idea. 500,000? 1 million? Okay, so all these routers see this withdrawal. And the withdrawal doesn't happen linearly. You're going to have a race to the finish line, so it's going to go really fast through all the Junipers, and it's going to go really slow through all the Ciscos, and it's going to go at random speeds through everybody else. So you get massive flat damping and a big mess. Customer link returns. Maybe they've gone home for the evening, they come back next day because they work in the theory of, well, if we switch the router off, my network is secure when I go home. Sure, it is. They come back in the morning, switch it on, and everything should work again. So /23 starts ripping through the internet. Well, what happens? You get another race to the finish. All these attributes get flapped and bounced around, and people get suppressed even though they're announced. Internet may take 10 to 20 minutes longer to become visible. Well, visible by who? By the customer. No aggregate. ISP does not aggregate. And many people do that. They don't announce the aggregate. 10 to 20 minutes longer to become visible, even longer. It's like, you know, if you sort of walk into the room when you come back from work, walk into your house, switch on the light and it kind of flickers, then goes out. Then maybe 10 minutes later, it flickers again, then goes out. I mean, you wouldn't put up with that service from the electricity company. So why, if you're trying to run a business level internet, why do so many people do this? And then I get all emails from the very same people saying, oh yeah, we're trying to do rate limiting QoS stuff on my Cisco routers, and what are the configuration commands or the semi-configuration? Does this massive long thing work? Or, hey, we're going to deploy MPLS in our network. You can't even get the basic stuff right. So why? Anyway. So, whereas this is how it should be done, which is my friend there was saying. Announce the aggregate. If you announce just the aggregate, the customer can do whatever they like. They can switch the router on and off as much as they want. The internet doesn't have to see. The internet should not have to care about some of this stuff. So this is why announcing the aggregate is really, really important, and not leaking the IBGP out. Even if you're announcing sub-prefixes to try and do your traffic engineering, your sub-prefixes for traffic engineering should not depend on what address space you've given to your customer. So you generate your traffic engineering sub-prefixes within your own network. Okay? That's what most people are trying to do these days. And that way they keep the network stable and internet independent of customers. And the thing is here, when the switches the router off, he comes back next day, switches it on, he starts his browser up, he downloads his email. It just works. It's the way it should be. Okay, good example is what people should be doing. Bad example is what too many are doing. This was done, when did I do these slides? I did these final slides about 2 weeks ago. The internet routing table has grown almost 2,000 prefixes since I did these slides. It's about 1,500 prefixes. When I did them, it was 220,947. My view is now 222,400 and something. Yes, in 10 days. Scary. One thing I do, I take the BGP table and I aggregate it by origin AS, just to see what it would really look like. I'm not taking account into any of the holes and so forth, so this could be a lot better. Jeff Houston in the CIDR report does a lot better job than I do, but I use this because it's a reasonable example. But even if I did the aggregation, same origin AS, I can pull the internet routing table down by 103,000 prefixes. So 103,000 prefixes of useless information there. It's almost half the table. Number of unique prefixes, 107,000. Okay, so that's even small. That's ignoring origin AS. Number of /24 is 117,000. Only 5,762 are from the 192 address space that was the official part of Class C when that all started. And this number has been more or less constant for about the last 7 years, 8 years or so. More or less constant. So this is always a favorite blame point. Sorry, 25,200 autonomous systems. Another number. So there's a swamp space. We always call the swamp space the 192/8 address space. So it's certainly 94, 95. Big effort to clean up the swamp. Because when we're running out of the former Class B space, ISPs got chunks of Class Cs. They would get 32 Class Cs or something from IANA. And so there was a big push to try and encourage people to aggregate these Class Cs together to a larger announcement. So that big effort reduced the table. It's about 9,000 Class Cs, reduced to about 5,500 from the former 192/8 address block. But unfortunately, the registry space, as well as the legacy space, is showing creeping aggregation. So this is 1999, February 99, when I started doing this stuff. So registry blocks contribute about 88% of the internet routing table. Pick some examples. I know back then that 193/8 and 194/8, 193, I think both of those are European, so RIPE NCC address blocks that were handed out by the RIPE NCC. I know that these two blocks, back in 1999, were fully allocated. Okay, they're fully allocated to all the RIPE NCC members. So what happened to them? Well, we're now in 2007 when I last did this. 193, 5,704, 194, 4,652. Huh? How come? What's changed? Why? None of the allocations have changed at all. But it seems there's just this general deaggregations happening on what was perfectly stable address block space prior to 99. 99 was fully allocated. I don't know how much recycling of address space there's been since then. Probably not a lot from what the NCC tell me, but we've seen a doubling of the address space being announced from that particular block. Look at 202. This is APNIC. Is it APNIC? Yeah. Is it? No. No, 203 is APNIC. 202 is ARIN. 203, I think, is APNIC space. Look what that's gone up to, 10,459 addresses pure with 203 numbers at the beginning, which is a shocking amount. I mean, if you look back, 203 was 3,622. If you look at a lot of the other registry /8s, what's happening to them? We're all heading like 5,000 or 6,000 kind of space, and you're looking through all these /8s that are being handed out. So there's a huge amount of deaggregation happening. So each registry block, I'm being generous, 5,000 prefixes, it's more like 10,000, but 5,000 prefixes maybe. Existing 81/8s going to make 405,000 announcements. Router vendors don't care. Well, we're being told that ISPs don't care either, so fine. By the time we've run out of V4 space, we could be up this size. I would say an awful lot more, probably 1 million prefixes in the V4 routing table. Yes, So what are the reasons? Oh, everybody justifies this as traffic engineering. As the AFNOG meeting last month in Nigeria, and when I did the deaggregation internet falling apart presentation, people said, oh, but we're doing traffic engineering. And so I threw up some examples on the screen and said, well, why are these guys all announcing the same /24? All consecutive, and it's all this path. And if you look on route views, you only ever see that path. You don't see anything else. Oh, well, but it's probably traffic engineering you don't see. Well, if I don't see it, who on earth is going to see it? Okay? So this is lame. I mean, yes, there's traffic engineering needed, but it's a minor percentage of the problem. The real reason's this. Okay, I'll jump through this. I mean, I figure out, I don't know. This would be a really, really good research topic for folks who've got time or the desire to actually look at it. How much of the deaggregation is actually caused by traffic engineering? I mean, this is back of the envelope stuff. I think probably 10% is due to traffic engineering, and the rest is just people don't care. Okay, so the CIDR report, if you don't know the CIDR report, again, Jeff emails that to the NANOG list every week that I put from that. It's really useful. It's got a website. You can go to the website now and basically pop in your AS number, and you see some of the results from that. Computes the size of the routing table, assuming ISPs performed optimal aggregation. Jeff basically, I think he takes the route views view, and so he sees different ways into the different networks. So you can do a much better estimate of deaggregation than I can with my single view. Obviously, you can do a much better one. So that's pretty handy. The website allows searches and computations of aggregation to be made on an AS basis. So it very effectively goes against the traffic engineering excuse. It's good proof. So let's have a look at the CIDR report. These are just the web page I just dumped a few days ago. Okay, 28th of May was a few days ago. So his view, 219,000 prefixes. If you aggregate, 140,000. So there's 70,000 there, 80,000 there that are just junk. Okay, about the same number of AS as you see, slightly fewer, and so forth. First page, second page, aggregation summary. So there are the top de-aggregators out on the internet today. So there's usual lists of suspects. I'm not going to name names, but the folks who are on there know that they're on there. Some of them are quite happy to be there. Others don't understand what I'm trying to prove. Others have got business reasons for being there, etc. But you see, if you look at it, there's some pretty spectacular savings that can be made. You know, one example, 1,010 could be de-aggregated down to 31, for example. So the 979 are due just to that organization. Look at, say, this one, announcing 1,257. They could reduce it down to 316. And if you look at what that AS actually produces, well, the way they've done the address assignment, they've split the network into all the different provinces. And they've given /16s to each province, or small n16. But it comes out of the same address block, and it's announced by the same AS. But they don't aggregate. They give each province their own visibility on the internet. We don't need it, because it doesn't appear in the traffic engineering at all. We've got loads of usual suspects. Anyway, I'm not going to go through them. Don't have time. But you see, there are lots there. So top 20 added routes this week per origin AS. So Uninet SA to CV has added 65 prefixes for whatever reason. So that's the sort of thing. It sees the activity that's happened. I mentioned these guys a couple of weeks ago, and somehow managed to remove 143 prefixes. I don't know if that was my fault or something else was broken, but anyway. More specifics. So these guys are announcing 1,299 more specifics than the aggregate they're announcing. So 7 prefixes, what they could reduce it down to if they tried. So they're probably quite happy to be number 1 in the LACNIC region routing table, but they could go down to about number 300 if they tried. And so on. So these guys could do a lot of cleaning up quite easily. And then you go right to the bottom of the website. You can pop your AS number in, and it will actually do aggregation recommendations. So I've taken AS4134 that I mentioned before, and I've popped them in and asked the CIDR report what I can do. And AS4134 can do all this stuff. They can announce this /15 and get rid of these two 17s and that 16. These aren't traffic engineering. you look anywhere on the internet, you pretty much see the path 4134. This is 4637 going to reach. Reach doesn't see any other path to get to 4134. So why do we need to see all this stuff? And so on. You can go through this list. It's a huge list of all the aggregation that's actually feasible here. I've done 18566. I mean, spectacular stuff. You know, the aggregate's being announced, but then we see 23s, 24s, 21s, 23s, loads and loads and loads and loads and loads. Okay, so aggregation potential. The routing table's up to here today. If we aggregate by AS path, it would come down to there. If we aggregate by AS origin, it's still under 100,000 prefixes. So if you care, if people care, you can reduce the size of the routing table quite quickly. Notice its nice exponential curve. Those of you around in 1992, 1993 will remember the nice exponential curve back then.
Consider like putting together a prefix list and things that are already added, there's no need to so I would say
Okay, the question is there a list of prefixes which, well, not to listen to, in other words, they're already aggregated and so forth? Well, not really, not really. And I can't really think of good ways of, well, I suppose you could use a CIDR report to sort of produce a list of, well, this is all you really need to. I know some ISPs decide not to listen to junk. And I know from the vendor side, we've been asked to do stuff like, well, if you see the aggregate, then ignore the sub-prefixes. But then how would you use that properly to not break intended multi-homing? Somebody may announce the aggregate as well as a sub-prefix because they're trying to do load balancing, which is fine. How far does this load balancing need to go? And there are actually better solutions to that particular issue, because trying to do this auto-aggregation, auto-dropping of things depending on something is really, I mean, there's been a discussion about it, certainly internally, and there's no good way of trying to do it that's going to be robust. But the tools are out there. There's a no-peer community attribute, which would be one useful thing. There's the AS path limit attribute, which is a proposed one, internet draft at the moment, which Joe Adley and a few others are trying to work through the system. That would be really, really, really useful, because then you'd set an AS path range. In other words, you announce a prefix, and you'd say, I only want this prefix to travel 5 ASs, or 4 ASs. And that's as far as it will go. And once the AS path limit counter has gone to 0, then you don't announce the prefix anymore. So those two would be fantastically good things to actually have implemented. Now, I was complaining about the no peer before. Maybe it needs a vendor implementation to actually get people to do it. With the AS path limit thing, I mean, it needs community consensus, at least within the IETF, and certainly here at NANOG to make that happen. And then, of course, the vendors need to actually implement it as well. I don't think there's an implementation yet of the AS path limit. But those two would certainly help. But again, it needs the operations community to do it. And I think it may, I mean, I don't know if people remember back far enough, but Sprint, when Sean Duran was there, certainly had a fairly violent filtering bit. Basically, his view was, well, if the registry is only allocating a /19, I'm only going to listen to /19. So he had a prefix list that said, right, I'm going to accept everything up to 19, anything from onwards, going to ignore. And I know there's some folks who do some things like that. They actually pay attention to the registry minimum allocation size, and that's all they accept. And they come along to these meetings and say, it's no problem for me. And we go like, well, what magic do you do? And that's what they do. They just basically filter on the registry minimum allocation. So the traffic engineering, they don't see, but it's not a problem for them. And of course, people who don't announce an aggregate don't get access to those networks. So it's probably going to need a bigger concerted community effort to do that style of filtering really to solve the problem. But at the moment, because the routers can handle 1 million fixes in BGP, in theory, people don't care. People aren't thinking about the whole BGP convergence thing, though. Because, okay, fine, your fastest and Junipers can converge BGP really, really quickly. You get your top-end PC running Quagga can converge BGP really quickly. But what about the guys who are using the smaller one-rack unit routers with the single sort of like 500 megahertz, 1 gigahertz router? Think about all these people who are still using last century's routers. There's still many, many parts of the internet still using last century's routers. They can't converge 10,000 BGP announcements in 5 minutes. So that's a big deal for them. So I don't know where it's all going. And it's good that you brought that up, because actually, three of us, it was Mike Hughes and Rob Evans, Mike from Links, of course, Rob Evans from UCANA, the UK Academic Network, and I got together, and we did this. We did an aggregation recommendation document, again, part of the routing working groups. That's been reviewed by the community and by the industry as well. So it's RIPE 399 document. We'll come up with some of the problems caused by deaggregation. Some of the solutions, well, in fact, we think we've got all the solutions, so it actually addresses what I've just talked about here just now. So that's well worth reading. So I've been going around places and talking about that particular presentation well, as much as I can. So it makes a difference, but I don't know how much difference it will actually make. The thing is, it's not a problem at the moment, and I feel a little bit like a person saying, oh, well, the sky is falling. And I think once the route convergence issues really starts affecting people and the network is no longer stable, then people are going to seriously look at the number of prefixes that they're carting around. Again, if you can wade through all the NANOG discussion on IPv6 and so forth, the same is true in IPv6, because IPv6 introduces nothing new from the routing point of view. It's the same issue. We've got a lot bigger prefixes. So the problem could be a lot bigger than it can be with v4. Okay, last few slides. Receiving prefixes, you don't open the floodgates. You want to consider different scenarios. There are three different ones that I can identify. You're talking BGP with a customer, you're talking BGP with a peer, and you're talking BGP with an upstream. They are different. You don't just accept anything that they send you. Accept anything, you'll get anything. ISP should only accept prefixes which have been assigned or allocated to the downstream customer. So if it's their address space, whether you've given it to them or they've got it independently, so independent address space, that's all you should accept. Don't accept network 10 or 172.16 or any other things that they think they can actually send. Yes, I know customers come along with money and they pay their bills promptly, especially the bad ones. Well, bad in whatever sense, but they pay the money promptly. Here, write this address block. I only need to write it for 1 day. That's all that matters. And it's like, some people are quite happy just to accept the money, whereas others are like, well, a bit more careful. The ISP is not assigned address space to its customer. Check the registry database to see if this really belongs to the customer. So use the whois tool. So, for example, here I've looked up APNIC. Who is APNIC for this address block? And well, it actually is APNIC's address space. Okay, so if APNIC came along with that, this is fine. If Aaron came along with this and said, hey, please announce this address space, you would look it up and you say, hang about, this is for APNIC. Why do you want to announce it? Oh, well, we've taken over APNIC. And it's like, no. Okay? You need to check this stuff. There are many, many people who have no idea that you need to do this. As a service provider, check that what you're going to announce to the network is actually legitimate. There's no internet policeman. Nobody's going to come along and slap you on the hand for announcing address space that isn't yours. All that happens is you end up breaking somebody else's network. Okay, here's another example. Probably a bit difficult to see at the back. This address block actually belongs to UUNet in the UK. It belongs to, actually, it's used by UUNet in the UK. So if somebody else came along, or these guys came along and said, hey, please write this address space for me, you'd say no, because it's actually part of a bigger block belonging to these guys, and so on. Okay, when we go to a peer, they're an ISP with whom you agree to exchange prefixes you originate into the routing table, okay? Direct peer. So all you expect to get from them are prefixes that you agree as part of the peering agreement, and all you should be giving to them are prefixes that you all agree on as per the peering agreement. So if they decide to give you transit, don't accept this as a great thing, because their network transit's probably not as good as yours. I mean, if it's better than yours, then, well, maybe do it, but keep quiet or something. Okay, but generally, private peering is just that. Exchange the prefixes that you originate. Okay. Agree what you announce to each other. Well, there's email documentation, part of the peering agreement. You send email updates, however you want to do it. Some people use the Internet Routing Registry, use configuration tools like the IRR toolset. I mentioned that earlier. If you're interested in that kind of thing, it can make configuration management a little bit easier. Some ISPs have their own registry set up just to manage the customer connections. They're nice tools. Well, I don't know how nice they are, but they're reasonably nice tools, at least they were a few years ago, to manage that. Produces router configurations that you can just drop in and use. So it takes the pain out of trying to figure out what all the filters and policies should be. From the upstream provider, well, they're the ISP. You pay to give you transit to the whole internet. Yes, you can get the full internet routing table from them. Just get a router from your favorite vendor with lots and lots of memory and pay their hugely inflated memory prices, and you'll be happy, and they'll be happy too. Do you actually really want to get 222,000 prefixes? Are they useful? Well, if you're a transit provider yourself, it probably is. If you're at the edge of the internet, in other words, one of the, how many transit providers are there? Probably about 2,000 ASs provide transit. The other 23,000 are at the edge. So if you're one of the 23,000, you probably don't need the full internet routing table. If you're one of the 2,300, you probably do, because it gets pretty painful trying to multi-home with partial tables. So receiving prefixes from them is not really desirable unless it's necessary. So I don't cover that here. Multi-homing tutorial covers that. Look on 2 NANOGs ago website if you want to see how the multi-homing, how I talk through the multi-homing. So ask your upstream or transit provider to originate a default route. It's very, very simple. On the peering to you, they send you a default. Default means I know how to get to the whole internet. It's just as good as 222,000 prefixes, and it converges somewhat faster. Okay? It takes, well, it reduces convergence from orders of many minutes to maybe a second or less. So it's probably better to work with that. Or if some ISPs still won't do a default originate, so get them to announce one prefix that you can use as a default, and that works fine too. If you want the full table, be careful. Don't accept everything. No open door policy. Don't accept private address space. In fact, RFC 3330 lists some of the special use addresses. Some of them should be routed. Most of them should not. Actually, Rob Thomas and the Project Cymru have got a list of what is called bogons, address space which should not appear on the internet. Most ISPs for handling the full table will use Rob Thomas's list, okay, the Project Cymru list, as inbound prefix filter. So you don't want to accept your own prefixes. Why would you hear your own prefixes from somewhere else? Don't accept the default unless you need it and want it, because there's some ISPs who like announcing the default to the internet. Every now and then it pops up. This one is, well, debatable. Prefixes longer than /24. Argument being is that you never really see anything smaller than a, well, whatever you call it, smaller than a 24 on the internet. You're not going to see 25s or 26s or 27s, really. So a lot of ISPs will filter on the /24 boundary. But saying that, and if you don't, you'll still see a few of those. But it's a kind of magic, well, invisible wall, is that what I want to say? Or transparent wall, that you don't go 25, 26 for prefix announcements. So that's why you see so many /24s. So pay attention to the prefixes received from customers. Then life will generally be good for the local network as well as for the internet. So it's responsibility of all ISPs to be good internet citizens. Now, I've got to preparing the network bit, which I'm not going to go through. This is really taking you through the step of moving from all static routes to deploying OSPF and BGP, but I don't have time. The slides are there. They're pretty obvious, so apologies for that because I've only got about 5 minutes left. So we'll just jump through these. But it's generally a phased approach. It's quite simple to actually migrate the network. You know, again, when I'm helping ISPs move from static routes to using OSPF and BGP, I can do a lot of the work in like an hour or two. It's actually very, very straightforward because you can build the dynamic routing protocols on top of statics, because the statics will override the dynamic routing anyway. Static is usually the most, the lowest protocol distance. So you can basically deploy the IGP and BGP without any impact on the network. It's pulling out the static routes that the issues start, and that's usually the harder work to do. Okay, so I really want to finish this bit, so the last 12 slides or so, on some configuration tips. So it's passwords, tricks, templates, and so forth. So round about IBGP and IGPs, run IBGP between loopbacks, not between real interfaces. Then you don't suffer problems if the real interfaces go down. Your IBGP stays stable, it stays up. You let your OSPF take care of any network infrastructure problems. Make sure your IGP carries the /32s. What about the demarcation zone networks? Some people use unnumbered interfaces. You know, I don't know what it is on other vendors, but in iOS you can actually borrow an IP address from one interface and use it on lots of other interfaces, which can be handy. It saves a /30 for each customer point-to-point link. Many people use next hop self. What that does, it changes the eBGP next hop to be that of the local router, so you don't need to carry external point-to-point links around your backbone. Some people put the demarcation /30s into iBGP, and then they only announce these prefixes in a special community towards maybe the network management center or network operations center. And that way the NOC can manage all the point-to-point links to customers, but the rest of the backbone doesn't have to see them. Basically, keep demarcation out of the IGP. You only want OSPF ISRs to carry the point-to-point link addresses between the routers. That's it. Keep it small. Next hop self, as I said, it's used by many ISPs and edge routers. It's preferable to carry the /30s around. Reduces the size of the IGP even further. Many ISPs today actually consider this best practice. Again, I'm kind of having the debate of, well, should we really be teaching this by default from the start? But then again, people forget about the next hop, or they don't understand how the next hop attribute works, and when they come across it, it all just goes bad. So I generally teach, well, this is what the next hop does, this is how it works, these are the pitfalls. You work around the pitfalls by doing this. And so they see both sides of the particular coin. Some ISPs limit the AS path length, because some BGP implementations in the past have had problems with long AS paths. Things like, I only support up to 32 ASs in the path, and after that I overwrite some other memory and cause it to crash. Or others, I only support 256 in the path because I can't imagine ending using anything longer. Or, I only use 8-bit integer to carry my AS path counter. And, well, once we run out of numbers, it just overwrites somewhere else. We've had all that. Even using AS path prepends, it's not normal to see more than 20 ASs in a typical AS path in the Internet today. Internet's average is 5 ASs deep. On average, it's only 5 ASs deep. It's not very much at all. Here's some examples. Some announcements have ridiculous lengths. This one was on the former 6-bone, the former IPv6 test network. This was an implementation error, implementation bug, where one AS in this whole particular list basically wasn't dropping out an announcement, so it just ended up going round and round and round in circles. So that was a pretty serious one. It was an implementation error. This one here is an example of a 20-time prepend, AS16327. Hopefully they're not in the room. They're doing 20 times prepends. What's amazing is this is the only announcement in the whole Internet. Right? I've been around lots and lots of looking glasses, looking for other instances of 194.146.180/22, and there's nothing. This is the only one. Maybe they quite like appearing in my routing report as the longest AS path in the Internet. Who knows? Okay? So, if the implementation supports it, consider limiting the AS path length you will accept. Some folks are just setting to about 25 because they don't want to run into any bugs or weird things that the people are doing. Okay, it's just general safety stuff. The BGP TTL hack, I quite like this. I think this is quite a neat trick. RFC 3682. What that does is we set the time to live on the neighbor to 255. So the neighbor sets his BGP peering to router 1. He sets the packet going out TTL 255. Router 1 expects it to come in with a TTL of 254. Why? Well, if somebody's trying to attack your BGP session, he sits out here, he sends a packet with time to live 255. It's 254 here, it's 253 there. This guy says, 253. No, ignore that. It should be 254. It's a good way of protecting the BGP session. Okay? He can't set time to live 256, right? Which would be 0, which would mean that we'd never get out of the local box. So it's actually a really neat way of protecting the BGP session from external attack. So that's quite a nice one to implement. Again, not every router vendor has actually implemented this, but I think it's really neat. Both neighbors have to agree to use the feature. It's much easier to perform than MD5. MD5 is the password on the BGP session, which I'll cover next. Some people call it BTSH, the BGP TTL security hack. Provides security, in quotes, for the BGP sessions. Of course, you need packet filters. MD5 should be used just in case there are messages which slip through the hack. So this was talked about in the February 2003 NANOG. You want to go back to then when Dave Meyer did the presentation about it. It was basically Dave who worked this through the whole process and got an implementation done at Cisco and so forth. Templates. Templates are really good things. There's still many, many people who configure their routers live on the network and then wonder why things go wrong. They didn't keep a backup copy and everything breaks. If you build a template, you change a template, you apply it to all routers, you can get your operations management system to load it into the router or whatever, however you want to handle it. But having a template means you can keep your configuration consistent and do a sanity check before you upload it onto routers and break configurations. Vendor defaults tend not to be optimal or very useful for ISPs. Okay, vendors are stuck with trying to support every class of customer. At least from our side, it's kind of, yeah, we've got ISPs, we've got small ISPs, we've got big ISPs, we've got the global transit providers, we've got telcos, we've got commercial networks, we've got academic networks, we've got research networks, we've got small offices, we've got home businesses. They've all got different expectations of defaults. So trying to come up with a default that fits everybody doesn't work really too well. So ISPs tend to cook their own. In fact, what's happened is the good folks at Cymru have actually come up with BGP templates, which are generally agreed across the industry. Right? They've done it, I think, at least for Cisco and Juniper boxes. They welcome contributions from other implementations as well, because if they're generally agreed across the industry, then more of the industry can actually use them. So they've got eBGP and iBGP templates at least. I think they've got security stuff and all this kind of thing. So here's the iBGP one. Run iBGP from loopbacks. Use next hop self. So keep the demarcation zone and external point-to-point links out of IGP. Always send communities in iBGP, otherwise accidents will happen, especially the no export variety. Hardwire BGP to version 4. Being paranoid, but it pays to be paranoid on the internet, especially if you have an implementation that doesn't know what BGP version 3 is, or version 5. People try it just because they can. Use passwords on an iBGP session. It can be pretty necessary these days. It's a shared secret between you and your peer. If you don't have the correct MD5 hash, then the packets are ignored. So that generally can be a good thing. It keeps the bad guys away from trying to attack your BGP session. BGP damping is really bad. Don't do it. Remove private ASs. Really important. Okay, remove private ASs. Every now and then, if you look at my BGP report, you'll see private ASs popping up on the internet. Use filters with backups. Some people use AS-path filters and they back them up with prefix filters. Use a password agreed between you and your peer for the eBGP session as well. Use the TTL hack if you can support it. Maximum prefix tracking, which somebody was asking me about in the break, that can be useful as well. If you only expect 10 prefixes from your neighbor, when they suddenly send you 220,000, it might be a bit of a problem. You might want your router to tell you about that. So this will do it. Limit maximum AS path length. Log neighbor changes. Watch the logs. Tie them into your pager, for example. Or get your system to send you an SMS that there's a problem. Make the BGP administrative distance higher than that of any IGP. Otherwise, prefixes from outside your network could override your IGP. It has happened to me, therefore, it's up there. So, summary, use configuration templates, standardize the configuration, be aware of standard tricks to avoid compromise the BGP sessions. Remember, do anything to make life simple for you. Remember the lazy administrator thing? Lazy administrator is a good administrator because they set everything up so he doesn't have to do any work. This is all about scaling. All has 2 L's, not 3. This is all about scaling. If your network won't scale, then it won't be successful. I'm finished, and I'm only 2 minutes late.